Hey, good afternoon, everybody. It's Tim Vasquez. Decided to start up the live cast here. You can see it right here on the monitor. Got a high risk for Georgia and South Carolina there. All right, so we got things set up, and I'm checking out the weather, and we're gonna probably just kind of run through all the charts. And I have not actually looked at the weather very much today, so I'm gonna do kind of like a from the ground up look at how the forecast is put together, starting with the analysis. So let's do that. Let's go into the charts and take a look at what's going on. Okay, things pretty much start with the upper air, and we'll take a look at that real quick. We're going to go up to 250 millibars. That's going to be at about 25,000 feet. And there's the U.S. right there in Canada. You can see kind of a meridional pattern. Got a pretty strong ridge out there on the west coast. And jet stream all the way from Denver into Fort Worth, and then back up to Chicago like that. And there's a southern stream here that looks kind of like it's either a branch. Good grief, I wonder, I seem to be losing my voice here. This could be either a split of the polar front jet, or this could be a subtropical jet. And the best way to figure that out, we'll go to 500 millibars. Okay, so I don't really see a very well-defined jet in this area. So this possibly could be a subtropical jet in that area. There's the Man, my voice is shot for some reason here. We're going to run this back to about 1415Z. And you can see a lot of what looks like isolated cells over southern Alabama right there. And they've been pushing eastward during the day towards the Macon area and western Georgia there. Guys, if you don't mind, I'm going to take a break and try to figure out what's going on with my voice here. Maybe I need to get some water here. So we're going to take a break, and I'll be back shortly.
Explain why you left me then. Would it help me understand? Now all I know is, oh that I do miss, oh that I do miss you. I don't know if I'll see you again, if I'll see you when you're finished with them. No, I don't know if I'll see you once more. I will be forever yours, I will be forever yours.
All right, I think this sounds a little bit better. I did a little bit of vocal exercises here, and I think I've kind of cleared up some of that. Very strange there. So, why don't we take a look at the radar? This is kind of where the action is. It looks like that's mostly south of Macon, Georgia there. So, already have a tornado warning out. Saw one earlier on this cell south of Macon. And what I like to do is I like to look at the warnings and see if I can pick up any information on there. So what I look for is stuff like whether spotters are actually seeing the tornado. So the source here, radar indicated rotation. So it doesn't appear we have a confirmed tornado on that storm at this time. This other cell here, radar indicated rotation. So in a way that's kind of good. Doesn't sound like we have a damaging tornado on the ground or anything like that. That appears to be about the only tornado activity except for this area near Sumter, South Carolina. And I know that there's an Air Force base just north of here. I wonder if the storm is moving directly towards them. I don't know. Looks pretty close there. That's Shaw Air Force Base, SHAW, right in that area there. And the tornado warning on this storm, radar indicated. Okay. So we've got a good picture of where the storms are. Doesn't look like we have any isolated, discrete supercell activity at this point, although the line does have kind of a broken character here. So let's take a look at the surface chart and get a look at the air masses, the boundaries, because that's very important stuff on a day like this. Okay, so for this I'm going to bring up digital atmosphere, and I'm going to pull down some of the latest data for 3 p.m. Eastern. Okay, I'll try to get that centered on the southeast here. So this is going to give us a synoptic scale picture of what's going on here. And it appears we're pretty deep in a tropical air mass, possibly well north of Georgia there. So we've got low and mid 70s in Virginia. It does look like we have boundaries in Georgia from this ongoing convection, so the wind flow is a little bit disrupted in this area here. Okay, then when we go further west into Mississippi and Tennessee, I suspect that the air mass origin here is from Texas and Oklahoma. So this is probably a different air mass in this region right here. The tropical air with the deepest, richest moisture looks like that's mostly south of this line right here. You can see when we go north of there, Virginia, 50s and 40s for dew points in that area. So this is probably a little bit of recycled polar air in that region right there. And the true tropical surge is down in this region right here. And of course the synoptic scale low pressure system, that's in western Illinois, just north of St. Louis there. So our fronts, let's see, that front probably, I don't know, we got something going on right there. Let's see, 85, 78, 66. You can see we're cooling down as we go west along this line in Mississippi and Arkansas. Some of the colder air, as a matter of fact, is right there in Arkansas. So I think we have the cold front kind of bowing out like that towards this this area here in Tennessee and Kentucky. And then where's our warm front? We got 80 in West Virginia there, and 69 in Columbus, and 60 at Findlay, Ohio. So our warm front is going to be located about right here. You see that? We go from 72 around Evansville here and down into 50s just north of that right there. Okay, so that's pretty cut and dry. And we can see that the cluster of storms in Georgia appears to be kind of out on its own out there. Okay, let's move to some of the other charts and see what we got going on. Again, we're building an analysis of, we're building a picture of the ingredients that we have over Georgia today. So we're looking at surface patterns, upper air, and starting to put everything together. Let's look at our thickness chart real quick. And this will kind of confirm what we saw there on the surface chart there. So we can see the temperature gradients here pretty clearly. And this supports the cold front that we drew there in Mississippi. So there it is. There's that cold front. And then the warm front is just north of there. Kind of like that right there. And our area of thunderstorms in Georgia right there ahead of the cold front. Okay. So when we look at the soundings around that area, we'll have a better idea of what's going on. So let's look at a couple soundings here, and I think the first one that I'll pull up is going to be Atlanta. Okay, let's see. I may have to go over to UCAR to get the soundings. Now, I think Birmingham is actually coming up there, so there we go. That's kind of an interesting feature there at Birmingham. This is what we would see with a cold front down just to the south of the station. So here it looks like we have some sort of cold air mass, In this case, it's probably outflow air. And the tops of that is about right there. So this is cool air, and you can see the humidity increases, or I should say the humidity remains pretty high as we go up towards the inversion itself right there. Then above that, some steep lapse rates right through 850 to 700 right there. A little bit of warm air, and we don't have a good picture what's up at the higher altitudes. But you can see here a very strong southwesterly flow there at Birmingham. And even down at 850, looks like a pretty good low-level jet right there. 50-knot winds out of the southwest. And that's probably a good idea. Let's check out the low-level jet. So this is the Canadian surface analysis, or 850 millibar analysis for 12Z. So this is 7 in the morning. And we're up at 850 millibars, so this is going to be 5,000 feet. And you can see there, right there at Birmingham, 40-knot winds right there. So maybe a little bit of a jet right there. Very veered. So this is probably bringing some drier air actually from the west here. So this is probably not really tapping the Gulf like what we see with our classic low-level jet situations there. Okay, let's take a look at dynamics, and I'm going to go to the NAM for that. Okay, so this is at 500 millibars. We're looking at heights and vorticity here. And this panel right there is about right now. So you're probably very familiar with drawing out the jet. So it's going to fall right there, just to the right of this cyclonic vorticity right here. So the flow here is very channeled. We don't have very many waves working around that trough. Looks like we have some stronger flow here over Alabama and Mississippi. So this is probably a result of being in close proximity to this jet here. Kind of a broad jet. And on those other charts, we were looking at the subtropical jet out in this area right here. And it appears that what's happening now is we're getting more of the polar front jet dynamics, and we're seeing the stronger winds kind of deepening through a deeper and deeper layer. So it started out with a subtropical jet way up there at about 30 to 40,000 feet, and now we're seeing very strong winds all the way down to 15,000 feet and even lower there. Okay, we'll look at the 850 millibar chart again, and we're going to look at the NAM version of that. And this is just showing us the setup just off the surface. Okay, so that's right now. So do you see the 850 millibar cold front? There's one on there. I don't know if any of you can find it. I'll give you probably 20 or 30 seconds to take a close look at that and see if you can pinpoint where that front is. And we're talking about the area south of the low in Missouri. Man, I'm glad I'm getting my voice back. I thought I had laryngitis or something going on there. Much better. Okay. That front, let me see if anybody commented on that. Nothing right there. But the 850 millibar front from about the Nashville area right now through Jackson and then down to Beaumont. So there it is right there. Okay, let me go back and take a look at chat, a little bit of discussion about tornadoes. Let's see, Ryan Toomey's said tornado emergency posted for Crisp and Wilcox. Okay, let me go back to the radar and check that out real quick. I do not know any of the towns very well in Georgia, so I guess we're talking about this right here. I see Crisp in here. So this is a radar indicated rotation on that storm. Okay, let's see where that rotation is. It looks like we're gonna really be depending on the velocity products to kind of fill us in here on what's going on. And the first thing that we have to do when we're looking at this area, we have to know where the radar is. A lot of times you can just look at the shapes of the pixels here. We can see this line here of range folding, and that kind of points to here. So the radar, we know that that's right up here. Okay, excuse me. The red is always positive velocity or outbound, and green is always negative velocity, and that's going to be inbound. So this is going towards the radar, or it has a component of motion towards the radar like that, and this has a component of motion away like that. So we've got this zone here of cyclonic vorticity right there. Spectrum width there showing a very well-defined line, and this is probably the outflow boundary right there. So do you see how awesome this spectrum width is? And it's kind of a shame that a lot of the tools we have for looking at NexRad radar, they don't have this. And even in a radar scope, which I use a lot, I don't believe they have spectrum width in that either. So this can definitely help you. And as far as finding your outflow boundaries and stuff like that, you can also find debris when you have a tornado. And if it's embedded in rain or it's very hard to pick out, that can kind of clue you in. That can be another thing to look at. Okay, I'm going to set a dot on this line here. So I put that right there. And we can kind of compare that with the reflectivity. So it looks like we have a outflow boundary, kind of like that. And it's actually pretty close to the storm. If the storm was gusting out and very outflow dominant, we would probably find the boundary way out here, about 5 to 10 miles ahead of the storm. So the main threat that we're looking for is basically a spin up of vorticity along this cyclonic zone right there. So along that axis, you see how it comes right through that dot? This kind of shows you the shear on either side of that line right there. So we've got one little zone right here of higher velocity. And I'm seeing about, let me set this up where you can see the scale. Okay, so down here at the bottom, We've got this readout. There's the velocity right there. It's going to be the figure on the left. And you can see we're seeing 47, 46 knots inbound right there. We don't see very much outbound motion right here. It's very weak. So if we actually want to evaluate this area right here, it's better to use the storm relative velocity. So what that'll do is that'll kind of subtract out the motion of the storm, and you'll see the velocities in this go down and this will go up. So there we go. We switched over to storm relative velocity, and I haven't set a motion vector yet, so let me do that real quick. Okay, there we go. I used the warning to set that up. I used the storm motion that it had here. So there it is, 250 at 24, so we're going with that right there. So we got about 17 knots outbound, and here we've got 35 inbound, so that's not very strong, but you know, that is also something, that's certainly something to watch right there. So here's another zone of a little bit of vorticity. There's the spectrum width again, and then we go back to the base reflectivity right there. Okay, then our next storm on up the line near Dublin here. You can see that the stronger reflectivity gradients in this storm, they're kind of concentrated here in the middle of the cluster. We don't have too much of those gradients setting up ahead of the storm, closer to the inflow region. So this storm here does not look very organized. But it is showing a bit of rotation there, so you see that right there. There's the storm relative velocity. And it does have a mesocyclone right there. So there's one part of the couplet right there, and there's the other. And the diameter on that couplet, about 5 miles. So it's a very wide meso. And motion here, we're seeing about 36 outbound and about 38 in, so that's a good 70 knots of shear. And I'm going to set the dot in the center of that meso. And now you kind of get a better idea what's going on here. So this here is the updraft region. And then back here we've got kind of an RFD structure going on. That right there. So you see how that kind of works when you put everything together. Spectrum width, that helps us kind of find the outflow boundary. So I'll put a dot right there and bring up the reflectivity. And you can see that that boundary is probably just ahead of this area of higher reflectivity. Okay, guys, let me go to the chat here and see who we got. Got Ryan Toomies and Fred Reamer up in North Dakota. Jeremy Mattingly's here. Alexi. And Mick, or Mike. Fred Reamer is in meteorological instrumentation, and his class is watching. Awesome. Ryan says the Weston, Georgia storm hit 54,000 feet. Yeah, that's certainly pretty good. And the tropopause in that area very high today because of the location. If I bring up the 250 millibar chart, you can see that the main polar front jet well to the north, so Georgia is pretty deep in this tropical air mass. So that you're going to find the tropopause a lot higher in that region. Megan John is here, and Ahmed from Saudi Arabia checking in. And Mike Estwick, he says, watch your model products. SPC alerted that the models were running too dry, moisture-wise. Chris Lasakis is here. And I'm just kind of going through chat right here. I probably can't read all of this, but let me scan through here real quick. Thomas Copeland, check it in. And David Holcomb. And Alexi, he says, Alexi says, would it look different if you're looking at it from a different radar? And I'm wondering if that's a question about this cell right here. And yeah, you know, these cells will look a little bit different depending on the path of the beam. Maybe you attenuate some of the beam as it goes through some of these cells, and you'll get kind of a different presentation. That can certainly affect the wave train right there. And in fact, the only product that's really immune to that kind of attenuation is KDP right here. So this is a product that kind of uses the phase changes as the wave train goes through these cells. And no matter how much attenuation there is, it will always pick up the same basic pattern. It'll be pretty reliable there. So in a flash flooding situation where you have a lot of training or a lot of cells and you're having to cut through a line like that, you can certainly go back to KDP to find if there's any cells that are not being detected very well by base reflectivity. Okay, we got a little bit of intensification of this storm here south of Dublin. You can see earlier I was talking about how the reflectivity gradients were kind of in this area here and not in the inflow region, and it looks like that's changed. We're seeing the features kind of coming together here. Okay, sorry about that. So there's the inflow region showing up very well there. And here's that RFD. So it's starting to take on the classic supercell shape. Storm relative velocity showing the circulation tightening up a bit here. Got about 42 knots outbound here, 44. And on the other side, we've got about 40 in. So this is about 80 knots of rotation. And here's another aspect that I'll show you. Keep in mind that the radar is up here, up in this direction here. So I'm going to draw the radar beam like that. Now, if we take the highest velocities on either side like that and draw a line, you see how there's a little bit of slope there. It's not perfectly perpendicular to the beam. So any thoughts what that means? that's something you'll want to look at. Well, keep in mind that if you have a couplet like this that's perfectly perpendicular, and it's a cyclonic couplet maybe, if it's perfectly perpendicular like that, that means you have pure convergent or pure rotation. On the other hand, if your couplet is oriented like that, so it's parallel to the radar beam, that means you have either convergence or divergence, one of the two. So if we have red outbounds right here and green inbounds right there, that would be a convergent signature. So we're actually seeing a little bit of that right here. So the radar beam is right here. So due to the fact that the maximum inbound is a little bit closer to the radar like that, and the maximum inbound is a little bit further away, that means that the couplet has a little bit of a convergent component. A little bit, I don't know if that's a good word. Basically what you have there is you have cyclonic rotation with a bit of convergence. And that can be significant because that's what you're going to have in the run-up to tornadogenesis. In fact, a lot of times in Oklahoma, when I saw large tornadoes coming together, for a few radar scans, I would see an area of pure convergence close to the meso. And that would eventually kind of work itself out and become very, very tight rotation. So when you see convergence, just keep in mind that that is pretty significant, and that can mean some important changes going on in the storm. Okay, they put out a tornado warning. So there it is. Radar indicated rotation. And we've got about 45 knots outbound here and about 40 inbound. So we're looking at about 80 knots of rotation. This is a meso. And if you were out here, I think you would probably see a good rain-free base and a wall cloud in this area here. And I'm not too sure about a tornado just yet. I'm not seeing really any tight rotation or tight shear. Probably in this area, that's an area I would probably watch right here. So you can see that kind of corresponds there to the tip of the hook. So there's the RFD. And there's the outflow boundary along the forward flank downdraft. This is the updraft. It's got kind of an HP-ish structure for sure. And then this suspect area, very tight rotation, located right there. Okay, my voice is sounding like quite a mess, so I'm going to take another break here, and what I do is a little bit of vocal exercises to kind of loosen things up, and that'll definitely help a lot. So I'm going to put up I'll put up the radar on the storm. I'll kind of leave it there, and I'll probably be back in about 4 minutes. So we will check it out then.
We're still running.
Okay, guys, I think I might have gotten that sorted out. I'm starting to sound like Sergeant Highway from Heartbreak Ridge for a while there. All right, check out our storm here. Wonder how many of you are running GR level 2 or GR level 3 also. I'm sure probably a lot of you. It's kind of fun coming together and checking this stuff out. Let's see here. We're seeing the circulation kind of holding about the same as what we saw about 5 minutes ago. Got some stronger rotation in the higher levels of the storm. This is up at 4,600 feet. So here's the maximum outbound showing 45 knots. And on the other side, we got 52 there. So that's close to about 100 knots. So we got a pretty strong meso up there just off the ground. So this is about 2.5 miles in diameter. I'm going to put a dot here in the center of that meso. And it's got a very classic structure there. There's the meso, and you can see we're bringing in the updraft, the inflow from the south. Getting wrapped up into that meso, and then on the back side, the rear flank downdraft. There's kind of a notch there of low reflectivity on the back side. And this is the RFD right there, the leading edge. So here you can certainly get some straight line wind damage. You've got the motion of the storm coupled with the rotational component of the wind. So this is kind of a prime area to get some very strong winds. Okay, as we go to higher tilts, we're going to watch this updraft area. I'm going to put a marker there, go up to 1.8. And we can see kind of a beware, very weak beware up here near, this is only up at 6,000. And it may or may not be in this area here. I'm not too sure the storm is strong enough for a beware like that to hit 20 to 30,000 feet like we see on the plains. The beware in the Joplin storm back in 2011, I think that was 2011 or 2012, that reached close to about 35,000 feet. It went way up there. And the circulation itself, the meso, 100 knots, 100 to 150, all the way up to 30 to 35,000 feet also. So if you had a pilot that was attempting to punch that storm and fly through it, they would be in some serious trouble. Okay, let me just check out, see if anything else is going on here. I think that is that's the big storm of the day right there, southeast of Macon. And does anybody know if we have any chasers on that storm? I'd imagine it'd be very difficult to chase in there with the traffic and the windy roads. That would be a mess there. Okay, let me take a look at chat here. I don't know where to put this window. Kevin McKinney says the Udall tornado in the 1950s was missed because the old radar of that era could not see it through a storm blocking in the foreground. Huh. Let's see, Mike Bexley checking out, getting back to work there. David Holcomb says, starting to see blue CC values scattered about that area in the lowest tilt. Could that be winds blowing things about? I don't know. That was about 5 minutes ago there. I'm not sure if that still shows up. Correlation coefficient just showing just kind of a mass of high values, just showing the rain in this area. I don't see any very distinct features in here. Let's see, the meso located right there at 1953. Okay, that moved. Okay, there's correlation coefficient. I don't really think I see anything remarkable in there, so anyway. Ryan Toomey's 6 screens running there. SPC discussions as well. He said Ryan Toomey says Joplin is in 2011. Thanks. Alexi says he thinks Tim Reed is out there chasing. He says he can find out if anyone is out there. Yeah, that would be very interesting. Georgia is kind of a very strange place to chase, and when I did hardcore chasing, I think the furthest east I ever got was probably Texarkana. And when you get further east than that, that's what we call chainsaw territory. Okay, if anybody has any specific questions, let me put that a different way. If there's any charts or any analysis techniques you might want to go over, you can mention that, and I'll take a look at that. If not, we'll just kind of keep working through the situation. And probably what we would want to do on a storm like this, we can see it's continuing to move eastward. We might be interested in what the air mass is out like ahead of it, because that could certainly influence the strength of the storm over the next couple of hours, especially if you have some very high moisture, like if your moisture axis is out here, then that would mean intensification as that storm moves towards that axis. Okay, I'm taking a quick look at my preview monitor here. And I wanted to ask, are you guys able to see the marks that I'm drawing right here? Let me make a circle on the storm. My preview monitor, for some reason, is not showing that, so I don't know if it's filtering that out or what. But anyway, a good site to look at if we want to look at this area right here is to look at the SPC mesoscale analysis. So let's switch over to that. And there's the URL if you want to get to that. spc.noaa.gov/exper, and there's the mesoanalysis products in that list. In fact, let me show that to you. So you can see right here, I put in spc.noaa.gov/exper. And waiting for SPC, there it goes. And it's going to be about the 4th or 5th item down here, this mesoanalysis graphics. Okay. So you just click on the sector you want and bring that up. And this would be the area that we would be focusing on right here. Okay, the first product we can go to is the dew point plots, the isodrosotherms. So let me bring that up real quick. Trying to find where that is. Yeah, there it is, temperature, wind, dew point. And I think when we're looking at a scale this small, we probably actually need to go to the surface observations. So let me do that. Let me pull down the latest data. Right now it's right on the hour, so I'm not too sure that we have any plots. Let me draw a quick one for Texas. Yeah, it looks like we have plenty there. So I'm going to set up a sector here for Georgia real quick, and we'll take a look at the environment in that region. Okay, I probably need to go a little bit further west there. Okay, there we go. Okay, so I've set up a map for Georgia, and what I'll do is I'll put on the counties, and then I'll lock that map. And there we go, there's our plots. And probably what we should do also is plot the thunderstorms. So I'm going to go to this set next rad stations. So I'll pick these stations right here. And by the way, we're using a digital atmosphere. This is a program that I wrote. So for a while, this was my bread and butter. And there's the storms right there, just south of Macon, and you can see that the area that is critical to this storm here is this region right here. Now it looks like we have a bad plot there. I think that 80 over 80 is kind of ridiculous. So we'll look at the other plots right here. I can see we've got 70s around the Savannah area. Dew points slightly lower in this area, so that might indicate maybe a little bit of intensification as it goes eastward. And one thing that you'll notice here is that the winds look kind of veered. So they're not coming out of the southeast like we usually see in classic tornado situations. And this might be a good time to look at a hodograph. This is something that a lot of people ask me about. They want to know how to go about using the hodograph and how you find helicity on these diagrams. So what I'm going to do is I'm going to bring up one of those charts real quick. And I'll show you how to look at a model-derived hodograph for the area right out ahead of the storm. So we're at pivotal weather. I'm going to switch over to the high-resolution rapid refresh. And I'm going to set that area for the southeastern U.S. Okay, so this is the model forecast for about right now. Let's see, we're at 20Z. Yeah, this is correct. So you can kind of compare this to see how the models are doing. And let me go over to Ecology page real quick. And I'm going to switch this over and look at the large-scale radar pattern. So let's see, we've got kind of the main cluster here from the eastern Georgia area down into this region. So sorry, I don't really know all the cities. So I'm going to take that and kind of compare that with high resolution rapid refresh. Sorry, I'm trying to find out where my tab is for that. There we go. So it looks like we do have a little bit of a difference there. We actually have a area of thunderstorms kind of set up like that, with other clusters very strong in this area. So the HRRR is a little bit off on this two-hour forecast. So if we want to sample the air mass out ahead of it, we can certainly do that. We can drop a cursor over this and pull that up. And this will give us an idea what the environment is out ahead of these storms here. So there's our photograph right there. Hang on, let me use a little bit of throat spray, just a second. Okay, talking for 1 to 2 hours is not really my specialty, so just have to bear with me. So anyway, there's the model-derived sounding for the air mass out ahead of these storms here. So you see this area of curvature here. A little bit of curvature, but that's mostly up near 3 to 4 kilometers. The really critical layer for curvature and stretching out the photograph is from 0 through 1 here. Now, one really good thing that they've done on this photograph is they've labeled each of the points here. You can see 1, 2, 3, 4, 5. That's the altitude in kilometers. And that's very important because there are some model sites or sounding sites. Let me show you one. If we go to UCAR soundings, so you've probably seen these soundings on a lot of papers and websites. They give you a pretty good SQT here. They also give you this photograph in the upper left. And you can see a big problem here. None of the points are labeled. So where is this curvature? That could be way down at 2 kilometers. That could be up at 10 kilometers. We don't know. So these soundings or these photographs are really not very useful to me. So I like what they've done here on this photograph. So for those of you who are not familiar with photographs, I'll just give you a quick rundown. This is basically the winds aloft from the surface up to the upper tropopause right here. So this here is this here represents the ground right in the middle of the photograph. So if we want to know what the winds are at the surface, we just draw a vector from here to here, and we can see that the winds are out of the south moving towards the north at about 10 to 15 knots right there. So the wind's up at 1 kilometer, a little bit stronger. Same direction. At 3 kilometers, they're even stronger like that. But the actual turning, the change in direction doesn't occur till right here. So now the winds become more southwesterly, and then they become westerly at the top of the troposphere. So actually the length of this line right here, the longer it is, the more shear you have in the atmosphere. So that's pretty straightforward right there. We've also got a dot here for the storm. This is storm motion. In this case, it's the right-moving severe storm movement dot right here. So if we draw a vector from the ground to right there, we've got storm motion out of the west-southwest at about 30 knots right there. So to find the storm relative helicity, we just basically take this movement vector here. We draw a line out to 0 kilometers like that. We draw a line out to 1 kilometer like that, and that gives us the 0 through 1 storm relative helicity. So basically this area right here, the larger it is, the more storm relative helicity you have in that layer. And you can see right here they are drawing the 0 through 3 kilometer layer. But really I think the 0 through 1 layer is the most important one. So I like to really keep an eye on that right there. So what this is showing as far as tornado potential, it's showing that, yeah, we do have some helicity. So this area kind of swept out right there. That's some marginal to moderate helicity. But there's not really a lot of turning in the lowest layers. That's one of the problems we have today. And you can also see that the lighter the winds are, the more area you're going to sweep out. So say that dot right there at 0, say that the winds are calm. So we draw our dot there and connect that to our line, and we would sweep out a larger area. So helicity really goes up. So if we go to our charts, if we look at the area out ahead of the storm and we see light winds or easterly winds or backed winds, that means higher tornado potential, higher SRH. And that's the reason mesolows are so critical. So if we have a boundary like here that the storm is developing along, and there's lower pressures right there, and there's a wind field response to that, you're going to have higher storm relative helicities northeast of that low. And that means that your tornado potentials are going to go up, especially if that mesolow gets reinforced by upper level dynamics. So upper level waves working the area, that can produce a response that makes the area very favorable for tornadogenesis. Okay, let's go back and check the radar. There's our storm there crossing the interstate. Looks a little bit less organized right now. Storm relative helicity shows that storm relative velocity showing that the mesocyclone is still there, but it hasn't really intensified. It's still about the same, maybe a little bit weaker than what we saw earlier. And tornado warning, showing it's confirmed. So we've got spotters or law enforcement reporting a tornado on the ground right there. Instead of right there, probably in the past 5 or 10 minutes. So probably right here we had a tornado on the ground. So I'm going to set a dot right there in the middle of that mesocyclone. And you can kind of use that to relate that to the storm structure. Okay, let me take a look at the chat here and see what's going on. Ryan Toomey says that the are you saying the stream is cutting off and on? Yeah, I know that the internet is not too great here. We're on a 6 megabit per second connection, so maybe we're hammering it pretty good here. The products I'm downloading may be kind of taking a toll on that. Okay, Scum says no good surface flow today and bad dew points. So I don't think there will be any significant tornadoes today, maybe something small in a few hours, but I wouldn't bet on it. So throwing out a forecast there, so good to see different perspectives on this situation. Ryan says his friends in Albany can't catch a break this year. Michael Phelps is going on live and on and off Facebook. Ryan really on top of things, catching that watch that got updated. And Alexi shared this webcast and let the people know that if they're on the ground, to please feel free to come in and let us know what they're seeing. All right. Okay, let's see here. Okay, so basically not a whole lot going on right now. We've just got that one cell produced a tornado, confirmed tornado, and looks a little bit less organized here as it crosses the interstate. So I'm not seeing really anything that looks like a there's nothing here that really looks like a tornadic signature. I don't see any very tight shear on this chart right here. So that's not to say that there is not a tornado on the ground right now, but I'm not seeing anything here on this image that would indicate that. Okay, so we go up to higher values and we can see that the mesocyclone increases in intensity, which is pretty normal. So we go up to 3.1 and 4.0. You can see the rotation pretty much in that same area. Kind of like a big stovepipe of rotation all the way up into the tops of the storm up at 22,000 feet. And you can see here up at, this is up at 32,000 feet, we pick up anvil divergence. So you see right here, very strong outbound. So it looks like I lost all my upper air products above 5.0 degrees. I don't know what happened here. I was sitting here and the frame blanked out, and 5.0 is as high as I could get. I don't know. That was weird. Okay, so there's the latest frame on that storm coming out of the area just east of Dublin. And you can see it's got kind of a supercell structure right there. So the boundaries would probably look something like that. There's a little feature out ahead of it. You see that right there. We can look at spectrum width. And it looks like it's not really significant. You can see that the main boundaries are located right there. And again, I wish a lot of the providers would really start using that spectrum width. That's very good stuff. So I'm going to set the marker on that. Switch over to reflectivity. And we can see that the outflow is sitting there right ahead of the higher reflectivities like that. So this here looks like a bit of a little bit of convection getting pulled into that updraft. Let me see if that came from something. Let me run that back here. Yeah, it looks like a few cells developing out there in the updraft region. So kind of messy right there. I'd probably be concerned that this area of convection probably could be disrupting the updraft. So maybe we would be looking at this area starting to form in the next 20 or 30 minutes here. Okay, we'll take a look at a few other products. I guess we can take a bit of a break. I was doing a little bit of time lapse this morning here. So a little bit jumpy because I haven't rendered it, but this is what I saw this morning about 7 in the morning. Just some static Q working from west to east. Cold air advection and a little bit of moisture there. And I don't know how many of you have been working with the GOES-R stuff, the GOES 16. There's this Catchwomanvetter.com site. They've been carrying the GOES 16 data. And to my knowledge, that's the only source that I've seen of high-resolution GOES 16 data. And if you guys know of any other sources, I would really be interested to know that. Because this is the only one I know of here. And when I checked on this earlier, for some reason it wasn't showing any high-resolution GOES 16 data. So let me check this out real quick. Let's see the GOES 16 view of the convection. Okay. Yeah, you see this drop-down box. This Alter GOES satellite, I think that's the conventional, the older GOES satellite. You have to click on this Super HD to get the GOES 16. And yeah, looks like it's working there. So that brings up the GOES 16 data. And I can bring this down to the county level. This is in the Valdosta or Waycross area, southern Georgia. And this shows you the cumulus field. So we got it kind of set up into cloud streets. And this can be very critical for finding boundaries before convection goes up. So you want to be kind of combing these high-resolution satellite images early in the day. Now let me show you that trick how to bring up regional satellite data on this site, because you can see here it's kind of like county level. And then when you zoom out, you get this really wide view. So the alternate way of looking at the satellite data here, you go down the list into this Rasterkarten. You click on Nord and South America. That'll bring up a slightly different interface, and you just zoom in on the area you want. And then we'll zoom in one more time. And this will give us satellite sectors that are a lot easier to work with. So instead of going from very tight to very wide views, you'll get the medium views. So it's a lot more suited for finding boundaries early in the day. So there you can see some of the overshooting tops right there in Georgia. And we'll zoom in on the Waycross area. And unfortunately, we have anvils covering the area where the inflow is. So this is the main storm of the day right there. And a lot of times we will want to look out ahead of that and see if maybe the storm is picking up on a boundary like that, perhaps. But we don't have any kind of view underneath this anvil canopy. Okay, so this is an example of the regional view that really works for finding boundaries. And this will give you the half-kilometer GO16 imagery. And as you can see here, they've got a frequency of every 5 minutes. So this is very good stuff. And I would recommend getting familiar with that. Let me take a look at the chat real quick and see if there are any comments about using the GO16 data. Maybe somebody has another source for it. Alexi says Ryan Corey is out in Alabama. Is he chasing Alabama? Kind of curious there. No comments about GO16. Oh, Dwayne Dunlap says College DuPage has GO16. Do they really? When I went there, I think the sectors looked pretty normal. Maybe there's a link I'm missing or something, but yeah, College DuPage, we should check that out and see if they have the data. Okay, so back to our storm right there. This is heading towards Swainsboro. Got a pretty well-defined RFD area right here. And this always means a possibility of wind when it's got a pattern like that, when it's very prominent, as you see right there. So we use base velocity, not the storm relative velocity. We use the base velocity for assessing wind potential. So here we can see a pretty good strong component of motion away from the radar right here, and that's measuring about 47 knots. So I don't know of a good rule of thumb for translating that to ground winds, but I would say that the lowest tilts here, when you're under 1,000 or 2,000 feet, that seems to kind of correspond to the highest gusts at the surface. So there's the outflow boundary right there, and showing up pretty well by the spectrum width. I think it would be pretty cool if they had an algorithm that kind of identified these features here. Areas of very high contrast on spectrum width, and maybe confirmed by velocity, and maybe it'd be kind of neat if that plotted it on the reflectivity chart. That would be a very, very helpful feature. Okay, other storms down the line, you can see it looks like we've got kind of a discrete appearance here. 3 main cells, and they've got this bow echo appearance, each one. So we would be kind of concerned about wind damage as these cells move through. They've each of those has some high wind potential there. So my voice is shifting into a Gunnery Sergeant Highway mode there. So let me drink some water and see if that helps it. Okay. Looks like we got a couple cells out ahead of the area. So there's one right here near the Valdosta area. So we would want to certainly keep an eye on these. So you can see here maximum tops on these storms up at about 37,000 feet. So this is definitely deep convection. And storm relative velocity is showing that we don't really have too much circulation except for this one storm, getting some pretty strong inbound here. Not too sure what would be causing that. Okay, so radar is up to the north, and we've got strong had pretty strong outbounds there. I wonder what would be causing that. It's very interesting. Yeah, because we would kind of expect maybe these young towers to be picking up some rotation. And we would kind of be expecting it to look like that right there. It's possible that the main updraft is out here. That's probably what's happening. So maybe the downdrafts, maybe this side, maybe that's kind of dry. So we're not getting any anything to scatter that area back to the radar. Okay. Back to those cells there. Let's see here. Let me check out the chat here and see what's going on. Okay, Kevin McKinney says cells are starting up aligned from central Kentucky to around Huntsville, Alabama. Maybe they will prove or provide something soon. Ryan Myers asks if anything severe expected for Ohio. Yeah, I'm not too sure. We haven't looked that far north. Oh, Fun with Tech has a link. I'm going to check that out in just a second. But let me take a quick look at Ohio. So I'll try to help out all the viewers where I can. And for that, I'm going to go to another chart here. Let me pull up a little bit of new data. Okay, we're waiting for that to ingest. Okay, so we bring up the latest plots right there, and we know we did our analysis earlier in the webcast. So we know there's a warm front somewhere just south of Pittsburgh and north of Cincinnati, north of Louisville, and the main low right there in the St. Louis area. And we, sorry, let me bring that a little further south. There's our warm front, main low right there. And we know that the cold front is somewhere around this region right here. So this is kind of a good exercise. You see how in Alabama we have 80s, 80 to 83, we have 85 in eastern Mississippi. So very warm temperatures in this area. And only when we cross over into western Mississippi, only then is when the temperatures go down. So we pick up low 60s and 50s right through that area. So that pretty clearly demarcates the front. So it's going through Mississippi. So a lot of people, when they look at the chart and don't really pay attention to detail, they would probably draw something like that, because they would be looking at the wind difference like that. And that's not what's happening at all. That's kind of a trough right there. So main cold front out in this area right here. So for Virginia, you can see that we don't have much moisture in that area. So you look at the dew points, and the dew points kind of tell you what kind of situation we have going on. You can see 47, 45 there. That's very dry. And for later, I don't know what's going to happen later. I guess I would have to look at the models. Maybe I'll take a look at the models and see what they've got going on. Okay, let me get rid of that photograph there, and we're going to switch the models to the Ohio Valley. And we're going to see what's going on with that low pressure system in the Louisville area. Okay, I've got to load the forecast loop, and then we should be ready. So you can see the time here at the top of the graph. Okay, so we do have a few showers out in Kentucky right there. And I think that's what, who was that, Kevin? I think Kevin was kind of alluding to that. Yeah, I think that might have been Kevin. Yeah, it was. Okay, so Kevin was pointing out these storms here that were starting to get going. Okay, so those spread out into Ohio later this evening right there. So these are probably associated with that frontal system. We know that the triple point for sure is somewhere in this area right here, because our analysis showed that the warm front was like that and the cold front was like that. So the triple point is kind of where you have some of the better moisture far to the northwest and in closer proximity to the stronger upper level dynamics. A lot of times, good grief, a lot of times the air mass to the, I'm going to blow out my vocal cords here. All right, hang on a second, let me grab some water. If anybody knows sign language, maybe we can switch to that. Kind of do our weathercast like PBS used to do with the lady there in the bottom left corner. Okay, I've got the dew point here. This is a good chart to kind of look at. 60s are indicated by the bluer shades. 50s are indicated by the darker green shades. So yeah, moisture is surging northward. And pretty much heading right towards the triple point area right there. So what happens is the moisture advection continues during the evening hours. And it kind of works eastward as the low pulls out to the east. And yeah, we do get some 50s there in Ohio, but you've got to have kind of an unusual situation to get severe, widespread severe weather with 50s dew points. You can do it in Colorado, but it's kind of tough in the eastern states right there. So you can see 50s dew points feeding any convection in that area. And I'll show you a very quick way to find severe weather. There's a box here in Pivotal Weather. You can go to the significant tornado parameter. So this kind of summarizes the best ingredients, where you have the lowest LCL, where you have the strongest shear, the strongest helicity, and the higher CAPE. So just by looking at this pattern, you can kind of assess very quickly where the environment is favorable for severe weather. Okay, so this is about right now, and we see some low values kind of working their way northward. And nothing really for Ohio here. Okay, a little bit of smudge in here. You see that right there? And the way we can analyze that is we can just click in the smudge area and bring up the photograph. And in the lower right, we have kind of a breakdown of the significant tornado parameter. And you can look down here and kind of see what's bumping up the numbers. So it looks like we got a little bit of CAPE, a little bit of moist air at the surface. And some shear there. Shear between the surface and the upper levels. That's the main contributor to any severe weather. And you can see that we've got a very long photograph there. Not much turning. So you can see our storm profile here. We try to sweep out an area. We get a very small slice here, so this is not going to support severe weather. This is what we call a straight line photograph. And this is very conducive to splitting storms. And a lot of times you will end up with a squall line once convection really gets going. Okay, I'm going to take a look at some of the other storms around the area. I'm going to do that using College DuPage. Okay, so I've got a sector up for them, and I'm going to have to move that. Okay, we'll take that to Tennessee and Kentucky, and we do have some cells going up there between Louisville all the way down to Nashville. And we haven't really assessed this area too well for severe weather potential. We've been kind of focused on Georgia there. So what I might do here is go to the charts, and I think what I need is a more detailed chart. So let me set up a chart here for the Kentucky-Tennessee area. Is anybody from the Tennessee-Kentucky area? I know we have some people in Indiana and Ohio. I know Sue and Sarah are there in Indiana, and we've got a couple there in Ohio. And let me bring up the county overlays. And I will lock that in. And dump the surface plots on the map, and there we go. So we see dew points in that area in the 50s. So moisture right now is a problem. So we can quickly trace out where the warm front is. Let's do that real quick. A little bit of frontal analysis here. So 81 degrees right there, very warm in western West Virginia. And we go to the north and things drop out to 72 in Columbus, 63 there in Akron. So very obvious where we have the temperature change right there. And we can bring that on through Cincinnati, 80 down to 76, and then sharply down to 70 here. Okay, and then the main low is going to be back in the St. Louis area. Looks like we kind of lose definition because of convection in this area. So basically, if we do have cells that go up, this boundary here would be important. So this is the area where cells are going up. Any cells that are interacting with the air in this area here, you can see that the winds are backed. We've got easterly winds right there, so that is going to add curvature to your hodograph. So if we were looking for severe weather potential, we would kind of probably take a close look at that region right there in southwestern Ohio. But again, moisture looks like it could be a problem. And I would have to look at the soundings really to know whether we could pull severe weather potential out of this. Okay, so since we can't do a detailed forecast, we'll just check out what SPC has. Watches, we've got basically a severe thunderstorm watch north of the Ohio River, and then south of that, tornado watches. So that's the deeper moisture there associated with those watches. And we can see the moderate risk kind of extending up there through Nashville and up towards Louisville. Okay, so yeah, that area definitely bears watching. Then we'll check out the mesoscale discussions. That kind of gives us an idea of what they're thinking in terms of changes. And so we've got this one. Let's see here. Okay, so that's going to be an old one right there. Okay, for any of you who are not familiar with convective outlooks, this is a high-risk day. And we don't have too many of these. And when we have high risk, see that right there? That is kind of that's very significant. That means there's the potential for widespread damaging storms. And I think Wikipedia has a list of high-risk days, and I'm pretty sure that I saw that in there about a year ago. So today would be one of those days thrown in that list. So you can see right here, basically, from Colombia down to just northeast of Valdosta in that high risk. Okay, let's see here. Let's go back to the radar. Severe thunderstorm watches on everything, including South Carolina. Got a pretty good isolated severe storm right here east of Birmingham. We'll have to keep an eye on that if it goes severe. I'm sorry, if it goes tornadic, I'll definitely go up there and check that out. So far, our cell of the day has been right here near Swainsboro. And we'll take a look at storm relative velocity and see what's going on. And it's continuing to keep that meso. See that right there? Very wide circulation. And it's almost perfectly perpendicular to the radar. So this is kind of pure rotation. So we're looking at about 32 out and about 46 in. So it is a little bit weaker than what we had about 30 minutes ago. Okay, let me take a quick look at the chat here, and it's fun to have everybody here as a group. This is kind of neat. I don't know if there's any other rooms that do this. I'm sure there are. I kind of got onto YouTube a little bit late. Started messing with it about a year ago. Let's see here. Yeah, that's right. Fun with Tech gave me a link to College of DuPage. Let's do that. I'll copy that into the browser. Okay, so this is the link that I got, and you can check that out. I'm going to copy that into a notepad, so if anybody wants to copy it down, they can. So after I'm done messing with the windows, I'll pull this up and let you guys look at that. So let's see where that takes us. Wow, looks pretty fancy already. Okay, so we've got a view of the U.S. right there, and a couple of sectors, or a long list of sectors. So let's see here. We'll click on Southeast U.S. and see what that does. So this is showing us infrared satellite imagery here. So this is the radiance, or the temperatures being emitted and picked up by the satellite there. So black is your higher temperatures. Here you can see the Gulf Stream. And then cold is going to be white. And the ability of the eye to discriminate a bunch of shades of white is very limited. So we use these enhancements to kind of get a better look at what's going on here. Okay, so let's see. How do we bring up visible? Oh yeah, bottom left. So there's this panel right here. We're going to switch that over to visible. Okay, so we can see that is GO16 data, so that's the GOES-R. And that's pretty cool. The only downside is we're kind of lacking the very tight high-res imagery, and that's really what's critical for finding boundaries. You have to go even tighter than this if it's possible. So that other site, Couchman Vector, it does let you do that. But let me take a look at this and see if there's any features I'm missing. Oh, this is cool. Look at that. Around Gulfport down to Slidell or New Orleans. Pretty cool line going up here. And it's probably in an area of unidirectional shear here, so these are probably going to stay non-severe. Okay, looks like there's no options to zoom in here, so there's one thing here that says Southwest US zoom. Let me see what that is. Okay, let me grab some water here real quick. Got my chroma key hanging on a curtain rod right there. Let me see if I can show that to you real quick. Okay. Yeah, there's a setup right there. So basically using a green piece of felt from Hobby Lobby. I think I need kind of a darker color. It's kind of white there. It's kind of difficult for the chroma key to superimpose against. So anyway, there's the setup, and I got my LaCroix, and I go through probably a case of this every day. Okay, so that's our College DuPage GO16 site. So looks very nice for kind of browsing around, and I would bet it's probably got that 5-minute interval. So let me check that out and see if it offers that. I'm going to go to the Southeast US sector. And hopefully this does not knock out the feed. I'm kind of concerned that bringing data down while I'm pumping all this video up may cause problems. So if it does, let me know. Okay, so I'm reading the times down here at the bottom, and I see that I'm getting frames every 5 minutes. That's very good. So yeah, that's very cool. So we have high temporal resolution. Okay, so the only thing we're missing is the very tight half-kilometer imagery. But other than that, this looks pretty cool, so I'm going to definitely bookmark this. And you guys probably want to know the site, so there's that right there. I'll leave that up for about 30 seconds or so. And I'll take a look at chat. Tornado at Newton, Georgia. Emergency manager reports house is damaged. Ryan says go to the German site Khur, Khur. So I'll take a look at that in just a minute. Cells popping up in Kentucky now, severe warned. From Ryan, he says South Indiana and South Illinois, severe warned. Warned. Mike Estwick mentions AM weather. Yeah, I loved that show. I used to watch that. It came on kind of too early for me. It used to come on like at 5:30 or 6 in the morning. And that was about when I had gone to bed. We would actually use that chasing in the old years, back when we didn't have all this technology, because they had a lot of the upper air charts. And there was no way to get that when you had no data back in the late 80s. So that upper data was really critical. And also, AM weather gave you the convective outlooks, and that was another key thing. And you can see how important that is, because nowadays when people are chasing, we make heavy use out of those convective outlooks. Okay, Ryan says, check the Georgia-Alabama line now. Okay, yeah, I'll do that. Kevin says, storm around Fayetteville, Tennessee has not taken long to require a thunderstorm warning. Kevin is east of Chattanooga. Yeah, I used to work with a meteorologist at the TV stations there, Tom Benson. I think he's a Chattanooga personality. He's the guy that hired me over at KTXS when I did weather there for a while back in the late 90s or mid-90s. Lexi says, thank you for the webcast, and it's very interesting. Yeah, I appreciate that. Check out the mess southeast there at NextLab from Robert Vermillion. And Jason Boggs says, just Google Go16 College DuPage and you'll see the high-resolution satellite image if you missed the link. Okay, so there's the link, and like Jason says, if you need it, just Google that in College DuPage. Okay, so back to our data here. And I think before I close this image, I'm going to take a look at this area here out to the east or the west. And I'm probably going to open one of these on that CouchmanVetter.com site. Okay, so I'm going to try Midwest U.S. Okay, so this is the north part of that area. And you can kind of see how the air is a lot drier in Ohio. So there's kind of a distinct lack of low clouds in that area. But we do pick up a little bit of that just east of Cincinnati there, enough to get some of these storms going here. Okay, let's see here. I'm going to bring Couchman Vetter over to northeast Georgia, so we have something to look at. So the way you navigate on this, you click near the edge of these sectors here. Okay, so you can kind of see the amount of detail that we get with these very tight sectors here. And I think you can even zoom in a little bit. And like I said, this is very important for finding boundaries early in the day. And about a week ago, I showed you the San Angelo storm using these animations. And it was pretty amazing how it picked up that boundary there. I can't remember what date that was. I think that might have been last Sunday. So definitely check that out if you get a chance. Okay, let's see. What's that other site that was mentioned? Let me go back here. German site Khur, Khur. Khur, Khur. Indian wild ass. Khur in Iran. Okay. I don't know. I'm probably going to need a link for that one. So if you send that along, we'll go check that out. Okay, I'm going to go over to SPC and go to this mesoanalysis page here. And I'm going to look at the CAPE. I want to kind of see the distribution of the instability here. I'm going to start with the surface-based CAPE. And so this is basically using the surface dew point and temperature. And we can see the highest values are in central Alabama right there. So I had no idea that that area was so primed back here. And pretty high values ahead of that cell of the day right here. We've got 2,500 just west of Savannah. Now let me see what it shows for most unstable CAPE. So this kind of accounts for elevated layers of very high moisture. Okay, so it looks about the same here. And the question that I'm asking myself right now is, if the CAPE is so high, why are we not getting storms in Alabama? Well, it's probably the cap. But let's check that out and see what's going on, because sometimes, we do get surprises. So to check that out, I don't know if you remember earlier in the webcast how I was showing you this, but you go to a good convective model like the high resolution rapid refresh. Okay, I guess that sector will work fine. And what you do is you drop the cursor on your area of interest. So I put that somewhere in central Alabama there. And it brings up a sounding and hodograph. And what does the sounding show? Let's check that out. Well, let's see here. Usually when we get convection, we kind of deal with a mixed layer. So we're going to kind of mix that right there. We're going to take the high temperature, 85, that looks about right on. Okay, so taking that into account, it doesn't look like we have too much of a cap there. So that's kind of strange there. Now the models did break out some precip, I think, here. Let me see here. Let me switch over to... I switch over to surface and precip here. Okay, so this is 19Z here. There's 20, 21. So the model is breaking out some convection in that area of high CAPE here. Doesn't really look very organized, just maybe some of this tail end stuff here in northeastern Alabama. And very linear as it moves out of Alabama into Georgia there. Okay, let's check out the air mass ahead of the line right here around Atlanta. I don't know if we have any viewers in Atlanta, but this would be for about 8 o'clock this evening. The high resolution rapid refresh thinks that there's going to be a line out to the west. So we drop the cursor in right in that area. And this kind of gives us the pre-storm environment. So let me set that up right there. You can see it's pretty weakly capped. Pretty good moisture out ahead of that line. So you see we start with a dew point of 63, and the shape of that moisture line right there is up and to the right a little bit. So that's an indication of some very deep, very rich, low-level moisture. And then above that we pick up the dry air. But one thing you see here is that the lapse rates are really not too steep. So that's going to kind of limit the instability there. And let's see what the capes are. It's going for 513 surface-based, 1,200 mixed layers. So yeah, the 1,000, that's kind of in the marginal severe weather range. Okay, then the hodograph, we see that we've got a lot of shear from 0 through 1 kilometer. And that can be very important in terms of convection. Because if the storm motion vector is sitting something like that, like if your cell slows down to maybe 20 knots, you're going to sweep out a very huge area here. So this indicates that we do have some potential there in Atlanta for severe weather. Now the only issue here is that a lot of it is being driven by the cold front. So you see right here along, that's the cold front picking up the storms. And the cold front kind of acts as a wedge, and it kind of reinforces the outflow with those storms. And it kind of cuts down the severe weather potential. You tend to get a lot of linear cell modes along that leading edge right there. So that's not very conducive for severe weather. We kind of count on these cells out ahead of the line. And it looks like the high resolution rapid refresh looks like it's going for a possible outcome like that. Little cell out ahead of the line. And that would probably be taken advantage of some of the high, low-level shear and curvature out in that area. Okay, back to our storm here. It looks like, let's see here, update that. Got a tornado warning on that, and it's got kind of a bow echo look here. So it looks a lot less like an HP Supercell and more like a bow echo. So we still look for some tornado potential, usually along the north edge of the storm here, along the leading edge. And we also watch this area back here for bookend vortexes. And then we do have the risk of wind damage, straight line wind damage out ahead of the line. Okay, tornado warning is radar indicated, but I'm sure there's spotters on that. And let's check out the other storms here. Looks like none of these are too organized. Okay. Now, yeah, look at Alabama here. This is out over the Anniston area, so let's switch the radar and take a look at this. So this is probably the cell out ahead of the line in that very favorable air that the models were hinting at, like I just showed you. Okay, we're loading the radar data. And let me take a look at that warning. Radar indicated rotation, moving east at 55 miles an hour. Okay, so there's our storm right there, and that's just south of Anniston. And right here, you can see the outflow out ahead of the storm. Spectrum width also showing it a little bit. Excuse me. And there's the presentation there on base velocity. So we're going to switch over. This is a fast-moving storm, so we do need to make use of storm relative velocity. And there we go. There's our classic mesocyclone signature. We've got about 34 out. No, what's going on here? Let me see here. Radar is down to the southwest. Why am I seeing outbound velocities here? This is showing outbound here and inbound. I guess our main cyclone is mesocyclone is down in this region right here. So I'll put it out right there. Yeah, see, I was looking at this and I was going, yeah, there's the mesocyclone. So there we go. So let's try again. Okay, 22 out and 34 in. So about 50 knots a shear there. And of course, we're going to find higher levels. We usually find higher levels aloft. So here we've got 69 knots out, and we've got about 17 in. But that's being strongly affected by the motion of the storm in the upper levels. So then we go up to higher levels, and we see that it becomes dominated by the anvil divergence. So here you can see very strong outbound velocities, and here we've got a little bit of inbound. And this corresponds to the back shear that you'll sometimes see on the anvils of severe storms. When you look at the anvils on the southwest side of the storm, and you see like knuckles and part of the anvil spreading southwest into the upper level wind, that's the back shear. So we see a little bit of that here. We've got light winds, very weak winds, kind of pushing southwest against the very strong upper level flow. And then over here we've got very strong outbound velocity. So this is the anvil spreading out in all directions here. So you can kind of use this to find the updraft. The updraft is going to be here producing all of those circulations that we see here. So that area right here is what we would be watching here. That's the updraft area. Okay. And there's the very tippy top of the storm up at 50,000 feet. Way up there. Okay, let me go over to chat, see what's going on here, and always have trouble finding my place when I come back to chat here. Tornado Chandler Jenkins, Georgia, from Ryan. Fun with Text says, nasty hook echo by Grayville, Illinois. Just tornado warned. Supercell east of Birmingham from Dwayne. Yeah, that's the one we just looked at. Ryan says, tonight the parameters keep the ingredients for Dixie Alley, North Alabama, and Tennessee area high. Cape and nocturnal activity. Robert says the College DuPage site, GO 16 that we just saw here, has a meso southeast, I think he means mesoscale, southeast view option today. Okay, so I guess that would be like a floating window. Yeah, I think I'll probably take a look at that. Dwayne says Supercell east of Birmingham has tornado warning. Okay, Ryan says, Tim, the Peachtree radar. Yeah, we could switch over to that, certainly. Robert asks, what color table are you using for velocities? Referring to this, I got these velocities from, let me see here. Let me pull up the name here. Sorry, I'm going to have to find... yeah, let's see here. Carl Berghoff. Yeah, I got these tables from him, viewer, and they're very, very helpful, and I think he might have acquired them from somewhere else. Some of these tables are floating around on the internet, and I know that some of the GR level 2 and 3 forums, they have some pretty good tables on some of those pages that you can download. And I get my tables from those. Okay. All right, so we're basically right now between the Birmingham and the Peachtree radar. So I guess at this point either one would be fine. And we were going to take a quick look at the GO16 satellite data from College DuPage. So let me bring that up and see if they have a special sector. Yeah, there's this meso southeast. Okay. So yeah, that I guess it brings us in a little bit closer. It's kind of, I guess this is kind of a floating window, and there it is, picking up that storm there east of Birmingham. And you can see how long the anvils are. So that's showing the very strong upper level flow, very good ventilation of the storm. And that kind of ventilation is very important for your storm modes. Sorry, guys. That wasn't a very good position. But anyway, there's those storms when you have very long anvils, very strong winds aloft. That will tend to favor LP modes. And when you have weakly ventilated storms, but you have all the ingredients there, otherwise like CAPE and all that, strong helicity, but your upper level storm relative, your anvil winds are weak, that's going to get you into the HP range, HP supercell. And that's the reason that College DuPage has this thing here on their soundings. Let me bring that up real quick. Okay, weather analysis tools. Okay, upper soundings, and let's see here. Oh, I'm sorry, guys. It was UCAR. Okay, you see this area right here, this donut. That's a indicator that helps to determine whether you're in the HP or classic or LP range. So you can see that it's kind of centered on the very top of the storm where the anvil is, right here at the end of this wind plot. So that's going to be upper level. And then here you have the storm motion here. So when you have a very long distance like that, that indicates that you have very high anvil level storm relative winds. So that's going to put you in the LP range. So the closer your movement vector is into the center of the donut, the closer you are to classic and LP modes. So when you're on there, now you know what that shading is for there. Okay, let's see here. I'm not too sure what product to use next. We don't have a whole lot going on with these storms. We got a couple tornado warnings, radar indicated, but no prominent hooks. This one is definitely looking pretty serious, though. You can see it's got that flying V shape right there. Very classic Supercell look. You can see we've got the very strong reflectivity gradient on the inflow side. I guess the inflow is probably more like that. And we're also getting that that curved appearance, indicating the presence of a mesocyclone in that storm. Okay, so there's our storm relative velocity right there. So how do you interpret this? Well, green is always inbound, so there's your inbound component. Then we have outbound like that right there. So what we're looking at for the updraft, we're looking for rotation like this. We're looking for cyclonic rotation, and we don't have that here. We've got kind of like anticyclonic shear. So where we're going to find that is going to be on this side here. Looks like we've got a little bit of strong motion away from the radar. So possibly in this area is where we would find the updraft. And you can also look at other tilts. Yeah, see how this comes together right there? Right here. Very strong gate-to-gate shear. So that's indicative of possibly something, I'm not sure if I would call it tornadic, but possibly some indicators leading to the run-up to tornado genesis here. So you see this pixel right here, we've got 75 out. We've got 10 in. So there's the center of the circulation. And if we want to kind of adjust this, you can see that this is a little bit weak on this side, very, very strong on that side. That's because of the storm motion at these higher elevations. This is up at 11,000 feet. And we can fix this by just changing the storm motion vector. We'll just increase this real quick. Now it looks, brought this up to 35. Okay, so it's starting to look a little bit more balanced here. 27 in, 62 out, and I think you could even go further with that. So there we go. That's starting to bring out some of the strong motion right in the area. See, that's probably it right there. So I brought the storm motion vector up to 50 knots, and you can kind of see that circulation right there. call from Domino's Pizza. Hang on a second.
strong. I waited up, wounds on my feet. Where will you be? Flickering through memories, the Polaroids yellowed in the sun, longing to be seen. So come and hide with me, hide with me, hide with me. Come and hide with me, hide with me, hide with me. Now the moon is full, the stars are bright. I call you up just to hear your voice on the machine. Nothing will be like it was, but you will always be my first choice, just as it seems. So I left the house broken. I walked these dirty streets for years. I left it all to see you, to wipe up all your tears. Will you hide with me, hide with me, hide with me. Come and hide with me, hide with me, hide with me. The sun is up, the clouds are gone, but I'm still here with wounds on my feet. Where will you be? If I left the house broken, I walked these dirty streets for years. I left it all to see you, to wipe up all your tears.
We were young and we were free and running, never bothered about what could be coming. Every day we danced and life was smiling. We were young and drunk in love. A few years later I have started thinking, if it's just love in every glass I'm drinking, we're like one and without you I'm sinking. I'm always shining next to you. Oh, I got you, there's no reason to chasing pavement on my own, 'cause you're here to stay every night and day. I'm delighted 'cause I got you.
I have always been afraid of changes, but you shown me life is full of faces. Sometimes clouds got in our favorite places, but we were young and unaware.
Oh, I got you, there's no reason to chasing pavement on my own, 'cause you're here to stay. Every day we dance and life's been smiling. We're not young, still drunk in love. Oh, I got you, there's no reason to chasing pavement on my own. 'Cause you're here to stay every night and day. I'm delighted 'cause I got you. La, 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 la.
Okay, guys, sorry about that. I'm trying to coordinate dinner plans and stuff like that. Shopping run, stuff. So, anyway, I'm probably going to have to take one more short break here shortly so I can, I'm going to place a Domino's order and get that brought in a little bit later. So, let's take a look at our storm here. Okay. Looks like we've had a kind of a loss of reflectivity gradient on this storm. You see how the storm has changed from earlier. We go all the way back here. Very strong reflectivity gradient on the south side there. Very well developed inflow area, updraft base. So something happened here to weaken it a bit. And that could just be something cyclical. Okay, so let's check out the rotation because that's another indicator how strong the storm is. Yeah, it looks like we're going to have to start switching over to Atlanta, the radar there. So checking this out real quick, we've got outbound velocities right here and inbound. And dimensions here are about what we would see for a mesocyclone. About 3.5 miles. We've got about 53 in, 32 out. That's still pretty stout. So, storm is certainly rotating. Certainly either certainly got some severe weather potential as it continues going east. So, the question is, what's going to happen when it gets to Atlanta here? It's only about 80 miles away or so there. So anyway, see what's going on elsewhere. Going back to our original storm of the day, that is pushed on off out in this area. It looks like it just has a severe warning. And we've got tornado warnings on these cells down here, but we're too far away to see them. The beam here shooting the tops at 41,000 feet. So that's all we're seeing right there. It's just the anvil on those storms. Then elsewhere, we've got one cell up near the Huntsville area, near, I think Redstone Arsenal is up there, I think. And it's got kind of a weak, kind of an LP-ish appearance there. Looks like it's kind of a young storm, kind of shallow. Not looks like it hasn't really picked up there. Anyway, yeah, the other thing here, you can see the anvil is really spreading out from these storms here. About 100 miles long. And one way we can kind of see this is on the cross sections. So I set up a cross section along the storm, along the anvil. And I think we're too far away from the radar to see that. Anyway. So what we would be looking at again, especially with the storm heading towards the Atlanta area, we would be looking at the moisture and the wind out ahead of the cell and any boundaries in the area. That would definitely have an effect on what happens to this storm as it moves eastward. So again, we can use some of our tools here, like digital atmosphere. Let me erase this, and I'm going to bring up some surface data. Okay, let me set a few stations here. Radar base reflectivity. Okay, so this kind of gives us an idea of the positions of these storms relative to these fields that we're analyzing. And we can see that we've got kind of an outflow situation out here around Atlanta. So easterly flow, and we've got cool temperatures, 60s, and that's quite a difference from what we have further south here. So yeah, there is definitely a boundary in this area. And probably the best way to find that is go out into the moist sector. Oh, I'm sorry, guys. Let me get rid of that. Okay, so you would go out to the moist sector and work your way from the center of the moist sector out towards the cold sector like that. And you kind of walk this mentally, and you would find that the air mass probably changes maybe right around here. So you kind of use that technique to kind of find your outflow boundaries. And the other thing that you can use is time series at these stations here. You can look at trends and find where the conditions have changed and what they were originally. So if we wanted to find time data for the station here, we can, in digital atmosphere, you can round it up and go to QC, like that. And you get the ICAO, so we have KCCO there. So from there, you can go to the Aviation Weather Center. They've got a good METAR interface. Okay, so that comes up, and we put our identifier in. And what you do is you ask for the most recent 12 hours. And you get the data. And now you can kind of look at all this to find where and when the air mass has changed. So you would look at sudden changes in temperature and wind. And we can see here that a thunderstorm came through earlier in the day at 16Z. That was about 11:30 in the morning. So that probably laid down some cold air. After it passed, we had this north wind. And then it looks like it might have shifted over to the east here. So predominantly east and east-southeast after that point right there. And then also you want to look at the pressure. You can find changes there. So we see the pressure fall very gradually. And then towards the top, looks like it bottoms out at the current hour right there. So that's kind of how you go about looking at this. And if you find a boundary, sometimes you can kind of link that up with other stations, and that'll kind of build a profile of what's happening in that area. So definitely looks like a little bit of rain-cooled air in this area, and that's not really conducive to supercells and tornadoes. So I think the best potential for any of that is it's got to be in this area right here. So I think that would be just south of Atlanta. I think that station there is Atlanta Hartsfield. Yep. Okay. Let me take a quick look at chat, and while I do that, I'll put on our radar. Storm is moving quickly already into Georgia, so I'm going to switch over to the Atlanta site. Okay, let me check it out here. Okay, yeah, I saw you guys mention the microphone problems earlier. Hopefully we didn't lose too much information there. I think that was before the break, maybe. Maybe I pushed a button or something like that. Let's see, discussing the radars in Atlanta there. And yeah, I was on the Birmingham radar, like Ryan said. Storm has slowed from 55 to 35 miles an hour from Ryan there. Yeah, that's... The slowing of the storm can be significant because that changes where the storm vector is on the hodograph. And that might put the motion into a better area to capture that helicity. Let me see if I can show an example of that. I'm going to go to the high resolution rapid refresh. Trying to find out where that is. Oh well, I'll just build it from the bookmarks. Pivotal weather. Oh, here it is. Okay, I'm going to try to pick up a hodograph in the Atlanta area. And it's interesting here at 21Z, it's picking up, looks like it's picking up that one storm there. And it looks like it has the axis of that through Alabama like that. So this looks a little bit better as far as positioning of the convection. So I'm going to put a forecast hodograph right there over the Atlanta area. And you can see that a slowdown of the cell would probably pull more helicity out of it. See here? If your storm is moving 55 knots towards the northeast like that, your helicity is going to kind of look like this. You're going to capture kind of like a ice cream cone shape, maybe kind of like that. But if you slow down, you get kind of a different shape there. Probably a little bit larger there, so that indicates a change there. So changes in the storm motion can have some pretty significant effects there. Pretty good hodograph there, and especially from 0 through 1 kilometer. So pretty ripe environment there for supercells. The big problem, of course, like I mentioned, is the temperature. There's a lot of rain-cooled air there, and the soundings here are showing it. Trying to see what this number is. I think 63 over 61. So you can't get a surface lifted parcel out of that. You would have to have either a warm parcel or you'd have to be lifting from an elevated layer like this. So, yeah, you probably could still get supercells in an environment like this, but I'm not really too sure what it takes to entrain the pool of cold air down below. I'm not too sure how much convection you can have above these cold pools before they start interfering with the updraft. That's kind of a good question there. I'm not really sure about that. So there you can see the very strong curvature of the hodograph, or the curvature of the wind profile. And there's the very high tropopause, way up there at about 40,000 feet. Okay. So a lot of good ingredients, and we would see the possibility of significant tornadoes on this storm to increase if it worked down that boundary. It moved more towards the warm air. So that's one question. If it moves northeast over Atlanta, it's going to kind of be in the rain-cooled air. So let's see, what's the track? Looks like it's kind of propagating east-southeast, maybe 100 degrees. Okay. Then we'll check out a little bit of our structure here. There's our storm. Inflow region, probably something like that. We go up to higher tilts. Let's see, one is, these frames are about 6 minutes apart, so not much continuity there, but let's see here. There's the tops, and we get one little speck there up at 44,000 feet. It's kind of a low top there. So anyway, there's an interesting structure there. This is up at 11,000 feet at 3.1 degrees. It's probably a little bit of that very strong upper level flow. It's probably being ducted somehow down to the surface. That might be what that is right there. Okay, so there's our storm. And we'll take a look at the reflectivity. There's the storm relative velocity, and I remember I was messing around with the values, so let me fix that. Okay. There we go. So there is our meso. So we got about 35 in and about 22 out. Not too strong, but it's certainly holding together. And you can kind of see the convergent component here. See how it crosses the axis of these two couplets are at an angle from the radar beam center line. So we've got a little bit of rotational convergence taking place here. And the center of that circulation is right there. We do have some consistency with the higher scans. Higher tilts are a little bit further to the west. That's probably a consequence of these scans here being a little bit older. Okay, but yeah, you can see the rotation there aloft. So there is a vertical consistency there, and let's check that out against the base velocity, or the reflectivity. So there's the center of the meso, and that's pretty close to where we find the rain-free base and the storm cell itself. Okay, let me take a quick look here at the chat, and let's see, Eddie W. checking in here. An active day. Yeah, May. When we get to May, that's really going to be something, I'm sure. Storm recycling from Ryan Toomey's looked very strong 10 minutes ago. And Robert asks, what's the storm slinky tell us on the sounding? That's a good question. I have not really paid much attention to that. He's talking about this thing right here. I'm not really too sure. I think that's probably a way of visualizing the shear in different layers, because you see from 0 to 1 kilometer we have kind of a, I'm sorry, hang on. There we go. So you see this here from 0 to 1 kilometer, you've got kind of a long length of that profile. So there's a very good shear in that layer. But here there's not very good shear because it's packed very close together. The wind direction and speed very similar from the top and bottom of that layer. So it's a very short segment. So maybe that's a way of visualizing the shear. When you have a long part of a color that kind of stands out, maybe that's a layer that has a very high shear and is significant for some reason. Okay. Let's take a look at one more sounding in the tropical air mass. This is a little further south. And we see a little bit less rotation there. This is kind of interesting. So a lot less shear here in the lowest 3 kilometers. And we can see a little bit more capping of the air mass here at about 750 millibars. So the storm slinky here looks like the red really stands out because that's the low levels. And then nothing standing out in the mid levels here, so no shear in that layer. And we can see that the dominant factor in storm in supercell development appears to be the low LCL, the high humidity. When you have LCL very high or very low, you have low storm bases, high relative humidities, and that is favorable for tornadogenesis. And we can see the values are a little bit elevated there on this sounding. Cape is also kind of significant. Not too high, 0.13, that's kind of in the mid-range, or that's kind of in the threshold range. SRH is very low, so it's brown here. And then bulk wind, that's pretty high, 0.26. And so we look at the photograph, and yeah, that matches up there. Very good shear, bulk shear. And very poor shear in the low levels. Very little turning. So that's not very favorable for supercell development. Okay, so there's our storm there. I'm going to have to take a break for just a few minutes. I've got to put in a pizza order. So let me do that real quick, and I'll just put on some music, and I will be back in just a few.
The sea and the wind and the flowers in my hair. You asked me again if I would go somewhere with you. Just the two of us traveling alone.
got you, and you got me too.
You can ride all the blue.
I wanna do what you want to. We can leave and run away someday, someday. I've been saving you. You save me too. Yeah, I need it. Don't you need me too? 'Cause I need you. Yeah, so call me anytime that you need a favor. Call me anytime I can come and sit in you. Oh, oh. Call me anytime that you need a friend. And call me anytime when you're at a tight end. You, I got you, and you got me too. We can always make it through. What we do is what we do. I can take you anywhere, somewhere. We won't be scared.
You will see me flying high. I'm staring into your blue eyes. We don't need nobody else. I got you, and you got me too.
I've been saving you. You save me too. Yeah, I need it. Don't you need me too? 'Cause I need you. Yeah, so call me anytime that you need a favor. Call me anytime I can come and sit in you. Oh, oh. Call me anytime that you need a friend. And call me anytime when you're at a tight end. You, I got you. You got me, got me. You got me, got me. You got me too. Got me, got me. I've been saving you. You save me too. Yeah, I need it. Don't you need it too? 'Cause I got you, and you got me too.
You say that you don't need me. You say let's take things slowly. I hope you realize you're playing with fire. I know what heartbreak feels like. I know I've shed some teardrops. I've been here before. You have done it now. Left me on the ground. This is it. I won't come back. If we don't stop,
Thank you for ordering Domino's. Stay tuned, and I'll show you exactly how we make your meal at your local
sitting by
Domino's.
myself, going
Thanks for
crazy
your
like all the time. If we don't
Thanks
stop,
for your help, Pizza Panel.
if I don't go,
The first
I've been
step
left
is
alone every night when you go. And I hope you realize, playing with the fire. Saying what's ain't easy. I know you can't talk to me, but I hope you realize you're playing with fire. You were my one and only until you left me lonely. I guess you stopped to care.
All right, guys, we are back. Okay, let me get my windows fixed here. Okay, we're continuing to review the weather situation there in Georgia and Alabama. And we've also got cells out in the Ohio Valley. So we go up to the north there. We've got tornado warnings out in eastern Tennessee there, north of Chattanooga. And we'll check out the warnings on this. And we've got radar indicated rotation. And these don't look these don't look very strong because we're using the Atlanta radar. This is pretty far away. We're just kind of using GR level 2's depiction of the tornado warnings to kind of see where everything is. So there's this one here, tornado warning for the Indianapolis area, or Indiana County. And they were showing radar indicated rotation. Okay, apparently we don't have a whole lot of widespread tornadoes today, so I guess that is certainly good news. But let's head out to Nashville and see what's going on there. We've been kind of stuck there at in Georgia for a little bit too long. So while that's coming up, I will take a look at the chat and see what people are talking about here. Kevin says the slinky has to do with, he thinks it has to do with something about the trajectory of the updraft. Yeah, I'm not too sure myself. That's a good question. There may be documentation on some of this code here that may just be a matter of Googling around to find out some information. Yep, place the pizza order, so that'll be coming in later. And let's see here. Got a lot of isolated storms out there between Nashville and Knoxville. So it's quite a large area. We don't have them all set up along a line. They're just kind of here and there. So we've got this one cell along the interstate. We've got a tornado warning on that, and again, that's radar indicated, and it looks kind of on the weak side there. Go up to the higher tilts, the intensity decreases. See, there's 20,000 feet, and it's gone at about 30,000 feet. So watching that again, this is the surface reflectivity. So we see about maybe 52 dBZs in the core. And you notice that it kind of holds on for maybe one or two scans and then it starts diminishing. So here we're losing the intensity. And then up in the upper parts of the storm, there's pretty much nothing up there. So that's a good example of a non-severe storm. And it probably was stronger when they had this tornado warning on it, but we'll check and see if there's any strong rotation in it, though. There's the storm relative velocity. And yeah, look at that. There's a little bit of motion right there. So looks like it did squeak out a bit of a mesocyclone in there. So we'll zoom in on that. So we're looking at the elevation of the scan. See on the bottom here, there's a readout showing how high the radar beam is, because we're a little ways away from the radar. So this is at about 5,000 feet. This is kind of a little bit high. This is like almost to right around the cloud base level. So pretty strong outbound right there. Some moderate inbound. And we're seeing about, let's see here, 64 out and about 26 in. Now that's kind of unbalanced, and when I see that, then I'll know that I need to adjust the motion vector. So this probably needs to come up to about maybe 30. See what that does. Okay, we're seeing 49 out and 43 in. Okay, so that's pretty good. And we've got some good gate-to-gate shear there. So yeah, this would certainly be indicative of a tornado here. So I'm pretty surprised a small storm like that could squeak out a tornado. But apparently it did. And there's that little bear's cage. So it's got a little bit of an HPS structure there. There's the updraft right there. And then we see a little bit of that B-weir right there. And this is up at about 10,000 feet. So main meso located right there. At this level, looks like most of the rotation is confined to this area right here. So I'm trying to find a vertical consistency here. So pretty good outbound there, pretty good inbound. I think here we just have kind of a wide meso here. And same thing right there. Okay, then above that we start picking up the anvil motions right there. So anyway, there's our cell. And that's what's going on in that one. Then we got a couple of more cells. This one is near Spencer, Tennessee. So that's going to be south of Sparta, southwest of Crossville. In the lower scans, it looks like this. Storm relative velocity brings out the motion right there. So higher outbounds are located right there. And remember, we have to keep in mind the radar is located in that direction right there. So that tells us that the meso, at least, is going to be kind of in this area right here. Looks pretty good on the 0.9. But we've got a convergent signature here. See that strong outbound right there? So if you start trying to draw these dipoles of circulation, they're going to be parallel to the radar beam. So we got to start thinking about convergence. This is probably convergence here. Kind of strange. I wonder what's going on there. This is up at 8,000 feet. And there again, a little bit of outbound right there. Let me put a dot right here where that strong inbound is. And we'll take a look at the reflectivity. And I think that's probably, maybe that's just part of the mesocyclone. So maybe, I was thinking maybe some rotation in the storm, kind of like that. I don't know, it's a good mystery right there. I'm not too sure what's going on. We could probably find out something by looking at previous scans. Oops. There we go. So previous scan looking like that. We could probably figure it out by looking at all that data there like that. 1.8 mostly showing some very strong outbound here, and this is where we start picking up the anvil signatures here. Okay, anybody else got tornado warnings? Not really. Looks like they put another warning out on this storm near the interstate and extended that northeastward. So man, it doesn't look very strong at all, but looks are deceiving. Storm relative velocity, do you see it here? Right there. So it looks like the inbound is kind of diminishing in this area. This outbound here is still hanging on pretty strong. Let me put a dot right there in the center of that. Okay, so there's that little bear's cage, little miniature bear's cage. And then we have our older scans right there. Okay, wonder if there's anything else interesting to look at. These cells further up the line in Kentucky, they look kind of boring. Looks like a lot of action in Ohio. Let's go up to Ohio and just check things out real quick. And I'll take a look at chat here. Let's see what's going on here. How are we looking in Carrollton? In Dallas? I think Dallas is cleared out. Had kind of a cold day here in Texas. Fun with Tech found a link to the Slinky at the WDTB site, the Warning Decision Training Branch in Norman. So there's a link there. Check out the chat. I'll just mention it for anybody watching the replay. It's wdtb.noaa.gov/build training with a T in training uppercase in#interactive/content/slinky.html. So Google could probably bring that up too. Dwayne says that if you right-click the warnings, you can get storm motion. Yeah, that's pretty awesome. I like that feature. So you right-click on a warning, you've got storm motion from the warning. So it pulls it right out of the text and applies that to your motion vector here. So that way your storm relative velocity values will look on point there. Okay, the storm came into cooler air. I guess we're talking about the Atlanta storm there. Uncle Step Back had the candles out and everything. Save the wax. Uncle Step Back says this is the 5th time where a tornado was supposed to be in the area and it goes over or under. We have a magic bubble and I love it, but prayers out to anybody dealing with it. Cincinnati getting interesting weather, according to Ryan. Where do you live, Uncle Step Back? I think I missed where the action is. Okay. Kevin says, check southeast Georgia, multiple tornado warnings there. Okay, let's finish up with Cincinnati, and then we'll go back down the line. Okay, things look pretty linear, kind of characteristic of cold air convection. A little bit of severe weather potential here. You can see the strong reflectivity gradients on the east side of this storm. We go up to higher tilts, and you can see the persistence of high intensities up here at 12,000 feet. We've still got 63 dBZs over Dayton. And you saw that right there, a little bit of white there at 19,000 feet, 70 dBZs. Yeah, this is a severe storm here. And then it tops out here at 28,000 feet. I'm sorry, 34. So does it have any circulation? Well, this is kind of a bad angle to be looking at the storm. See, the storm is kind of oriented like this. And the radar is trying to view it like that. And when we're trying to find tornadoes along squall lines, QLCS tornadoes, and if we're trying to assess wind damage, high wind potential behind the gust front, we really want to be looking at the storm kind of head on like that. So it gets kind of tricky trying to figure out what's going on. But we do see the convergence along the gust front. So this is all outbound air from the radar. This is all got a component of motion towards the radar. So in between is where we have the gust front. And we can see it there on spectrum width. And look at that, you can see it extends all the way down. Can't see it on reflectivity very well. See, you guys got to use this technology here. And I think we got to demand it from the radar scope guys and some of those other software authors. So there it is. I'll put a dot over this. And it's under there. And that's important because if you have a severe storm lurking out in this region here, that could pick up the boundary. So that's one reason you would have to keep an eye on these things. Storm's going over the Cincinnati area there. And kind of weaker, more disorganized storms into Kentucky. And now we'll go south to, I guess, Columbus, Georgia. Let's see, Moody and Robbins. I guess I got to pull up Alabama. Oh, Fort Rucker. I think that's the one. Okay, we've got tornado warnings on that stuff in southeast Georgia. Looks pretty quiet in the Alabama-Georgia area. And nothing on that cell in this area, so I guess that cold air did kill it. Okay. We're coming up blank for images from Fort Rucker. I had that problem earlier today. Something's wrong with that radar site. So I'm going to switch over to Atlanta for now. Let me check my text messages and see what's going on here. Okay, looking at the chat. Let's see here. What do we got going on in chat? Not much. It kind of quieted down there. Kevin Lamping says, Southeast Georgia, multiple tornado warnings there. Storm Spotter Mike says KEOX is down, and so is MXX. I don't know what MXX is. KVAX, that's Valdosta. KCOX is good. Calio Delphi says he's been hearing a lot of Doppler radars are out completely in the region, which is bad. Yeah, that's certainly bad timing there. Okay, it looks pretty quiet in southeast Georgia. We're observing this from the Atlanta radar. Our cell approaching Atlanta has died down. And that's because it has started entraining some of that cold air at the surface. And we saw that earlier when I put these plots up. This is Atlanta right here, and you see 63 over 71. And we'd have to wager that that air probably has some substantial depth. Or not depth. Okay. Resulting in the death of the storm. So yeah, this is all outflow. And I was showing you earlier how we have kind of an outflow boundary like that. So this storm here does have some potential if it can move down the boundary. I'm sorry, that was the one from earlier. So I guess we're talking about this storm here. If that can pick up that boundary, then that may have some potential there. Got a storm over the Birmingham, Alabama area. Using the Atlanta radar, we can see the tops on that are a little over 36,000 feet, so definitely some deep convection there. And then we have our storms in southeastern Georgia there. So I'm going to pull up the, I guess I'll pull up the CLX radar. Okay, let's see here. Looks like overall things have quieted down tonight, and I'm sitting here trying to think why that would be so. We haven't seen these storms really aggregate into a large MCS yet, so a lot of them are still kind of doing their own thing, kind of disorganized. Let me get some current radar data in here. Again, this is Digital Atmosphere. This is a program that I wrote. I started writing this in Korea when I was working at the weather facility there. So I started writing code to import METAR and plot maps with that. And I don't know if anybody remembers weather. What was that program called? It was called Weather Graphics with an X. That was a DOS program that I wrote back in 92 or 93. And that was really popular. It kind of did these maps, and there was nothing like it at the time. So a lot of that code was reused in Digital Atmosphere. Okay, set next rad station. I'm going to pull up all these sites here, and we'll get a big picture of what's happening across this area here. There we go. So now we're going to pull down the radar data. And we can see that coming in. Yeah, I was trying to show the status over here. The radar data coming in from the Weather Service, and there we go. There's the large-scale picture. This is kind of the playbook for what's happening this evening. So we've got isolated cells out in the Atlanta area. We've shown that this cell here kind of shut down from the cold air at the surface. These in southeast Georgia are continuing to push eastward. The air mass here is relatively undamaged. It's relatively losing my ability to think of a word here. I guess it's what happens when I'm sitting here for like 3 hours. All right, let's plot the surface data real quick. I'm going to load that real quick. So we're going to get the 6 p.m. Eastern surface data. And after this, I'm going to show you a couple of other products on the Pivotal Weather site, the model data that can help you forecast on a day like, on a night like tonight. There's a lot of tools that we can use when we go through the model data. But looking at the actual observed surface data, here's what we got here. You see all the IFR conditions in northern Georgia here. See, all this has something in common. It has easterly wind flow. It has IFR conditions. We have dew points near 60, temperatures near 60. So this is all an outflow pool from this large area of convection in the east part of the state. And I think we're probably seeing a little bit of that on the radar right there. So this storm crossed onto the wrong side of the tracks and is probably on its way to the big atmosphere in the sky. This one here has a little more potential because we can look at the plots and we can see that, well, we've got 72 dew points right here. We don't quite know what's going on in this region, but there could be 70s dew points there. And then we have problems out in this area here. Okay, so what happens to the cell really depends on how the moisture fields are set up out in this area here. Okay, then further south around Valdosta, let's see here. We have southerly flow. We have dew points from the mid-60s to the low 70s. So this is all relatively this is all pretty much pristine. I was trying to look for that same word again, sorry. Okay, so there we go. Let's switch over to SPC. And we'll take a look at the environment. See, what I'm doing here is kind of what the forecasters at the Weather Service would be doing when they're trying to analyze weather for their area. And this is also what a lot of the SPC forecasters would do too. This is how you would tackle this situation when you see the storms there on the radar and you're wondering what the trends are going to be over the next few hours. So it's a matter of picking out which tools are the right ones for the job here. Okay, so what would keep precip going overnight? What would keep the storms going for the next few hours? We would need a good moisture field. So let's check that out. Let's go to the temperature, wind, and dew point. Okay, so we get this field here. The red lines are temperature. The green line, or the blue lines with the blue dashed lines, those are dew point. And that's what's really critical to severe weather severe weather formation, to the development of thunderstorms. And we can probably find an axis in this chart here. And it looks like that's about right here. So you see what I'm doing with the blue lines? Blue lines are kind of extending like that. And it builds this moisture axis north from south central Alabama to northern Alabama. Well, that's not too good for eastern Alabama. It appears what has happened is this MCS here has scoured out the moisture. So a lot of that moisture here from Atlanta southward has probably been overturned. Now we do have these cells out in this region. We can look at the moisture axis out in that area. And we can see that, yeah, there is one through the Jacksonville area right there. So we would keep an eye on that location right there. And I think what we're seeing here is an outflow boundary kind of like that right there. So these cells have laid down this outflow pool, and their outflow boundary is looking kind of like that. So a lot of the severe weather potential for Alabama depends on what kind of upper level dynamics are moving toward the area. Short waves, jet streaks, higher wind speeds aloft. And also, if there's a response in the low levels, we would want to see pressure falls in this area. We'd want to see stronger winds. In this region right here, that would result in moisture advection, and that would boost these all into a big squall line or even isolated supercells. But I don't know if we have those ingredients. For a guess at what's going on, we can look at the high resolution rapid refresh. Actually, we need to look at the NAM for that one. Their HRRR does not give vorticity fields. Okay, so I'm going to go to NAM. And then I'm going to go to upper air and, upper air dynamics. Then 500 millibar heights and hang on, I got the wrong one. I was rushing. Okay, upper air dynamics and then 500 millibar heights and vorticity. It's going to be that one. So this tells us what kind of upper level lift is working on this area where we have the storms. Okay, so you can see that this is 18Z. So this is a... Hang on, let me fix this. Okay, so 18Z, that's earlier today. Then 21Z is when we started the webcast. We can see kind of a rough look in here. This is probably contamination from the storms out in that area. So it's not really possible to read these values due to the atmosphere that are being disrupted. But we can see this lobe right here, higher vorticity working its way eastward. Not very strong, but it is approaching the area 0Z. That's going to be in about 1 hour. So yeah, maybe there's a little bit of lift approaching central Alabama, central northern Alabama. And then here's the main spectacle out there in northern Mississippi. That's the main wave right there. So by high vorticity, you can see that this is a relative vorticity chart. This really should be an absolute vorticity chart. This isn't really what... anyway, that's a topic for another time. But vorticity, this measures the spin of the air. It measures curvature and shear. So here you can see the height lines have curvature. So the wind flow is also going to have curvature as it moves through there. So this is positive vorticity because of the cyclonic curvature. And also there's very strong shear. There's very weak winds back here. You can see that the height gradient is very weak back there. Here the height gradient is very tight. So in between there, you're going to have an area of shear. Very strong winds on that side, very weak winds on that side. So those are the contributors there to vorticity. And the other contributor is planetary rotation. And when we have that, we have what's called absolute vorticity. And that's what we use for upper air charts. Okay, so there's a little dynamics lesson, and hopefully that's a little bit helpful there. But so we've got maybe a little wave working in, and what I would like to do when I see stuff like that is look at some of the other models and see if they have a similar pattern. Nowadays we have the regional Canadian model. It's a good model. It's worth checking out. So it's also going for a little bit of some sort of weak low moving across Alabama. But it's very important to not get hung up on the details, on the very small scale details like this. Like very small features like that and like that. You're going to want to kind of look at just the general sense of what it's trying to show there. So maybe something in that region right there, but we're not going to get hung up on stuff like that right there. That's probably noise in the model field. And it looks like by 3Z, it looks like maybe some stronger dynamics start picking up here. Maybe with the approach of the trough there, the winds are going to be picking up. You're going to increase the shear, and that's probably intensifying the vorticity in that trough right there. So wow, big trough moving in here. This is going to be midnight. And that moves very quickly through the Atlanta area. So maximum impact of those upper level dynamics, that's going to be right around 6Z. That's going to be about 1 in the morning, 12, 1, 2 a.m. Very strong height falls. Strong vorticity advection, probably upward motion. So that makes me think about maybe a squall line developing out there in Alabama later on. Okay, and let's just see what it shows for precip. So again, this is the Canadian model, the Canadian regional. And we start out with 0Z, which is right now, and you can see that the model does not have too much detail in Georgia and South Carolina. So very vague fields there for the storms that we have there. But we can see what looks like maybe some intensification right there. See that right there in northeast Alabama? We go ahead 3 hours. Now we have what looks like discrete cells with a little bit higher intensities. And whatever that is, that moves in through the Atlanta area around midnight. And then it dissipates as the flow changes around to northwest. That's a very abrupt flow for 500 millibars. I'm sorry, yeah, 1,000. I think we're looking at surface pressure. Yeah, okay, I'm sorry. Yeah, this is surface pressure here. But the precip that I was showing you, that still applies there. So anyway, the cold front will be coming through Georgia later on. There it is. And then by 6 midnight, there it is right there. And a very strong surge of cold air. Look at that. This is midnight. We got 540 decameters moving out over Memphis, Little Rock, and northern Mississippi there. 540 is generally a rule of thumb for where your precip transitions over to snow. So that means that there's probably a good push of cold air coming in from the northwest there. Okay, then just northwest winds tomorrow. 540 line pushes south through Atlanta. And we've even got some snow showers in the Asheville area right there. Okay. Okay, we're still here. Still running through the charts. Let me take a look at the chat here. Unavailable. Yeah, that might have been the word I was looking for earlier. Robert says, your explanations are great, Tim. I learn every time I watch. Thank you for taking your time to bring this to us. Yeah, thank you. I appreciate those comments. It all makes this worthwhile. Okay. My chat is doing something weird here. Yeah. Oh, that's weird. It stopped. I was going to show. Yeah, I was going to show you guys what it's doing here. Okay, then it stops. Yeah, see that? It's been flashing. I was sitting here trying to read what you guys are writing, and it was just flashing on and off like that. Okay. I'm just going to copy it into Notepad. It's ridiculous. Let's see here. Notepad. And I'm going to read what you guys are saying. And let me put the radar up so you have something to look at. There's the radar out of the Savannah area. Dennis S. says, I agree, Robert. I've never had anybody explain like this. Thanks, Tim Vasquez. Appreciate that. And Patreon, yeah, if you, even a little bit of money would certainly help. So please do that if you get a chance to check that out. On the nightly video, the link to that is on there. And I think you can just go straight to patreon.com/MetLab. Oh, okay. Fun with Tech got that right. Okay. Let's see here. Andre from Australia checking in. Very good. Half the radar stations are out across the southern region. Yeah, it's pretty lame there. Okay. All right, let's see what else we got here. Looks like we formed up a little bit of an MCS across South Carolina here. None of these storms here look too severe. Looking at our basic principles of reflectivity gradients and high intensities and just your general shape of the cells, nothing particularly strong in here right now. But again, that's just, one snapshot in time. These were probably, parts of these storms may have looked a lot different a few minutes ago, for all I know. There's our tornado-warned cell over Reidsville in Claxton, Georgia. Switching over to storm relative velocity. Don't see anything too strong here. We've got this one little area of outbound. Kind of a strong area here too. So I think they may have been keying in on maybe something right there. So I put a little marker there, and that happens to be kind of where the hook echo would be. See that concavity? When you see a concavity in the area where the inflow region on the storm should be, that's an indicator that you may have rotation going on in that thing. So right there, I'm thinking that's probably the center of the circulation. Hang on a second. No. I'm sorry, I messed up. Okay, red is outbound. No, I'm sorry. Yeah, okay, that's right. Okay, I'm just making sure that that the sign of that rotation was correct. Anyway, we'll go up to higher levels and look for any circulations up there or nothing. Okay, so there's not too much vertical consistency on that area of shear right there. Looks like a little bit of rotation up here in this part of the storm. I'm going to put a dot right there. And on base reflectivity, looks like that's pretty well embedded in the core, whatever that is. And we see it up at higher levels right there. Yeah, I suspect this might have been what the weather service was keying in on right there. Let me back that up a little bit. So we see strong outbound right there. Okay. So very weak signature on that storm, and if anybody is in the Claxton area, I don't think I would worry too much, but just take your usual precautions. Some of these cells getting a little bit of a bow echo appearance, like what we see in Douglas. And the main area that was advised for that high-risk region, that was located here from Columbia down to just south of Macon. This was under a high risk earlier today. But now, that is all covered by outflow air. So probably a big meso high back here, and the storms are pushing clear of that area right there. Okay. Looking elsewhere around the country, all we've got is one tornado warning out in Tennessee right there. So things seem to be kind of winding down here a bit. Radar indicated rotation. Okay. Well, anything else we want to look at? I think I might be winding down here. So if anybody has any last requests, let me know, and we can certainly put that on. Okay, we'll check out the chat, which is still flashing on my screen here. Okay. Oh yeah, I think I've got a overlay here. Yeah, there you go. I forgot I had that card there. If you wanted to donate, you can certainly do that. And, like I said, that kind of offsets the time that I pour into this, because on a night like this, I would probably be programming or trying to get that book project started up. And this kind of makes it a little bit more sensible for me to spend the time to do the webcast. So, and that stuff pays my bills, so it's certainly appreciated. And I'm hoping to get symmetric DSL here, because my internet is only 6 megabits per second. I can only do 480p SD video. So if we get enough funds come in to put in symmetric DSL, we can do HD, 1080, and all that stuff, and do some great stuff. Okay. All right, looking at the chat here, let me check this out real quick, and let me put up some radar for you guys. Wow, these things are falling apart. I guess I'll take it up to Kentucky. Yeah, I guess we're going to go for maybe... Yeah, I guess I'll try Jackson. Yeah, Robert Vermillion remembers weather graphics. Now, who remembers radar scan? That was the predecessor to weather graphics, and I wrote that back in 1992. And that program originally took RCM radar data code and produced very coarse radar graphics. Let me show you this. This is what we had as hobbyists back in the 80s and 90s. RCM used 20 by 20 blocks, I think, for radar data pixels. Looks a little bit like that. But yeah, they used a RCM code starting in the late 60s to produce these radar maps. These radar maps have been produced continuously since the early 70s. And that was one of the first applications of using the coded data to actually plot visual graphics. They did that on those mainframes, and I'm trying to find an example of those maps. That was one. And that's another poor example, but let me just see if anything comes up for my software. I'm going to put in radar scan. Oh boy, yeah, there's my software there. I'm going to try just one more right here. I'm going to try weather graphics and RCM. I guess this stuff is getting too far back in time for the search engines to care much. Well, anyway, let's see. Let me put some weather data back on. Okay, so there's Jackson. Got a bit of a bow echo there, so let me get rid of my ugly mug. Okay. So this is certainly severe. We've got a very strong bowing of this echo here coming into the area north of Lexington. And this is a good application of using base velocity to assess the wind damage potential. The radar located right here, shooting the cell like that. So that's in a fairly good position for measuring the winds. So we switch over to base velocity. That gives us ground relative wind. And we can see what's behind the outflow boundary there. So let me set that up for you so you guys can see it. So this here, definitely the gust front. And then we measure the winds back behind there. We get 30 knots inbound. 45, 47. So that's probably going to be gusts of about, gusts up to about 30 or 40 behind this stuff. So let me put a dot here along that outflow boundary so you can switch over to reflectivity and kind of compare it. There's spectrum width. Use spectrum width, guys. Seriously. Shows up very, very prominently there. And part of that is probably because these boundaries loft up all kinds of particles, small bits of debris like microscopic size. Insects, that's a really big one. Some birds, and all of that scatters back to the radar, and they have very high diversity. There's a lot of different motion in there. Now, I don't think this shows up too well in reflectivity. So yeah, this isn't really exactly a matter of the energy coming back to the radar from birds and insects, but it hinges more on the diversity of motion in there. So let me see if I can bring up see here. I was checking to see if there was precip type, and yeah, I don't think GR level 2 carries that. But anyway, there it is right there. And it shows up at higher levels also. We got a cell out ahead of that line, and you can see that this looks like possibly a left mover. See the structure here, very unmistakable. Higher intensities close to the northern part of that storm. And if it is definitely a left mover, it should be moving kind of like that. Well, pretty close. Okay, then we can see how high that is. And that tops out at about 21,000 feet, so that is kind of a shallow convection there. Okay, so that's what's going on around that storm. Some of these other storms also have a bit of a bow echo shape going on. And other than that, not a whole lot going on, really. Okay, so let me park it there and take a look at chat, see what's going on. Okay, yeah, Robert Vermillion went over to Patreon, and I appreciate it very much when we do the nightly webcast. I'm not sure if I'm going to do one tonight or not, but I will try to thank everybody for that individually. Fresh cells popping up in Alabama again, line forming in the middle of the state. So that could be that upper level energy starting to come in, the higher wind speeds, and possibly the response at the surface to the height falls. So you get convergence at the surface and more cells developing there. Ryan mentions the mesoanalysis report at 6 p.m. I didn't see that. I'm trying to read this here. Wispy. Oh, okay, from Wispy. Temperatures here in Tennessee did not reach what they were supposed to. Too cool now. Carl Berghoff. I appreciate these color tables here. He says the warning colors need to be adjusted to avoid confusion. Okay. What's funny is I've kind of gotten used to this scheme here, but if it helps you all, I will go ahead and change that. Okay. Well, guys, I think that's probably about just about it. Let me go down to Alabama real quick and see what's going on, because I'm probably close to wrapping this up. And we will have a lot of fun with this on Supercell days, chase days on the Great Plains. I'll probably fire this up, and we'll try to follow what the chasers are doing out there, pull up some of their feeds, and That should be a bit of fun there. Okay, so there's our cells going up there between Birmingham and Atlanta. And I think this is that old cell that we had been watching back in Alabama a couple of hours ago. See, it's right there, passed over the downtown area. I'm pretty sure that that's it. And then we've got these newer cells starting to move in. So when you see this, this is a good time to go back and look at the temperature and moisture of the air mass. So you go back to digital atmosphere or now what you could do is you could use the SPC let me see if I can find that real quick. Okay, SPC XPER. Now to find out what's happening, like I showed you there across eastern Alabama, one way of doing it is going into the experimental mesoanalysis graphics, and you'd pull this up and try to see what has changed. But you have to keep in mind that this is built from model data, and the models are always running a little bit behind by like maybe a couple hours. And it shows you up at the top right. 1704, 05, 22. This is the 22Z model here. And it says the surface data is from 23Z. So all of this data is a little bit old here. Okay, surface, I think the surface applies to this right here. So that's going to be new right there. So that's 23Z, and right now it's 2321. But you can see the model data is about an hour old. So when you're looking at these fields here, like this one, this is a model-derived field showing moisture. And you remember when we went over this a little bit earlier, about 15 minutes ago. So if you try to base your forecast on what it's showing here, you might be a little bit late. So it's better to go into the observed surface data, like we're doing here. And you can use the digital atmosphere, or if you don't want to, you can use UCAR weather. In fact, I'll do that real quick. Go to UCAR weather, go to their surface reports, and you click on this map right here on the left, and click on MGM. That's the closest station, and you can use this to get the station plots here. Give me just a minute. I'm going to be back in just a second. I think the pizza is here, so I will be back in just a second.
I'm never giving up on you. I'm never giving up on you. This time I know we're really through. But I'm never giving up on you. I'm never giving up on you. I'm never giving
Okay, we're back here. All right, we're back. Let me bring my windows up here. Okay. Let me take a look at chat real quick. My chat window is flashing again. I think it's overloaded here. So I'll just switch this over to Notepad. Kevin McKinney says it was overcast for almost the whole day in the Chattanooga, Northwest Georgia area. And he thinks all the forecast discussions were expecting clear skies. Well, that's interesting because forecast busts like that, they're not too common, but they do happen. And a lot of times it's due to over-reliance on models. So I would be kind of curious what went wrong exactly. Carl says, well, actually, with the environment in place, with such extreme shear in place, it often overcomes lack of instability. In fact, more tornadoes are expected after dark. Yeah, and it should be mentioned that the low-level jet actually picks up at night, too. So that can certainly increase the shear. And there was a very noteworthy tornado from 1986. It was the Sweetwater, Texas tornado. And that happened at night. And very strong low-level jet. And there was a warm front and curved photographs and things. Things just went bad for that area. I guess storms formed northwest of San Angelo and moved into Sweetwater, and that was kind of a bad event there. Greg Kerner says, severe possible up here in Atlanta. Severe possible up in the upper Midwest Sunday, finally. Carl mentions he's been watching the models. Photographs could point to classic supercells on Sunday. Placement of the surface low is everything right now. Iowa. Yeah, this next system is taking a north track. Let me see if I can pull that up real quick. And for this, we have to go to the GFS. Okay, so there's our continental U.S. For GFS. And we'll go ahead and get a sneak peek of what's happening. So, yeah, that last break. So, smells pretty good here, so I'll probably be hacking into that in about 5 or 10 minutes after we wrap up. Okay, so we have our GFS run up, and let me get that switched off. Okay, so our system from Georgia moves northeast up the coast. And there it goes right there. Looks kind of like a nor'easter. Hang on a second. There we go. So there goes our northeast U.S. system up the coast. Very strong push of cold air on the backside. We've talked about the 540 line coming all the way down into Alabama. And there it is right there. Occluded low up in New York, so snow showers and actually some rain up there Friday. Then high pressure across the Great Plains here, and we develop a lee side trough. So you see how that's a trough right there, and there's no thickness gradient along it. You don't have this packing of thickness lines like you have like right here. So that trough falls right in the thermal ridge axis. So that kind of shows you that that's probably some adiabatic heating, and also you basically, this is where you have very strong flow aloft moving over the mountains, or very strong perpendicular component, and you end up with a lee side trough there. And you can get some very gusty winds depending on the on the pattern. So lee side trough moves out into Colorado and Kansas. There it is right there. Very warm. Here comes the next system working in through Wyoming and Southern California. So that works its way out into the South Dakota area, Nebraska, and the south part. Looks like it's moving through South Carolina, but I can see a few thickness lines out in Arizona, so it may be on the move eastward there. Okay, so here's their system there on Sunday in the Nebraska, Iowa, Minnesota, South Dakota area. So probably a chance of thunderstorms there on Sunday. Looks like a bit of a warm front right in this region right here. So when we see this, we look at the gradient. See down here in the Gulf, see a very strong gradient in here. We see that the Gulf is open, and we see that the majority of the moisture is heading up towards Iowa and Missouri. So best severe weather potential, if anything breaks out, is going to be probably right there in Iowa. Then after that, we see the cold front start to emerge. Warm front moves northward towards Lake Superior, and we have the tail end of the system right here into New Mexico and Arizona. This is Monday morning, the 10th, and we see that push eastward. And we get a bit of a squall line here. So that breaks up Monday morning. Looks like the air mass is probably just uncapped. So things go right up along that cold front, and those move eastward during the day. Okay, high pressure over the plains for the 12th on Wednesday. Then we have another chance of some thunderstorms in West Texas. And we can look at this to kind of see what the pattern is. We can see there's strong upslope. See that right there? High pressure in Missouri. We have a very strong easterly component. And we have moisture from the Gulf. Very rich moisture. So that spells cooling and destabilization. So by Wednesday, apparently, the model foresees convection around the Hobbs Midland area. Okay, so I was looking at this on Thursday. These storms don't really do much as they go east, and I think that's because of a lot of cool air, a lot of cool dry air being infused from the Ohio River Valley area. So as these storms move eastward, they're getting into progressively worse air. So nothing really moving eastward on the 13th, 14th, 15th. And looks like a front kind of in this area right here on the 17th. And there we go. Pretty busy polar front there from Lake Superior all the way down to Texas. So this probably spells out a good chance of thunderstorms. This is on the 18th, Tuesday. We can see the Gulf is wide open, and most of the flow is heading for Texas and Oklahoma. So this is a good setup for thunderstorms in that area. Then, of course, everything moves eastward gradually. And it looks like things really cool down around the 21st. Look at that, a lot of snow showing up in the Great Basin area and the Rockies. And the 540 line coming all the way down towards Bakersfield and Reno. Now, I remember earlier this winter, the model, the GFS, had a cold bias. I don't know if that's what this is. It could be, since this is 372 hours out. But who knows? This is probably quite a ways into the future there. So let's take one last look at the radar and see what's going on. We have multiple cells breaking out in the Atlanta, Birmingham area. Thunderstorm warnings on all of them, and one of them is taking on the supercell appearance here. Maybe two of them. Okay. Okay, let me take a look at chat here, and let's see. We've been doing this for 3 hours and 35 minutes. No, wait. 4 hours. 4 hours and 30 minutes. Good grief. Okay, let's see here. Yeah, I was going to grab chat real quick and see what you guys are talking about. Greg, Carl says, Greg, I've been watching the models. Photographs could point to classic supercells. On Sunday, placement of the surface low is everything right now. Greg says, South Iowa, looks like. Ryan says, thanks, Tim. Pizza Domino's, yep. Got a pizza craving going on here in the chat. All right, yeah. Let's see. Did I make Rayab too? No. Rayab was a program by John Shuchuk, and it's still under development. So it's still being worked on and improved, and that's it right there coming up. So I'll probably do a workshop on that sometime and show you how that works. Rayab is a pretty good tool when it comes to modifying soundings, and when you modify the soundings, you can really see the impact on CAPE and convective inhibition. And if you modify the photograph, you can kind of see how playing around with that changes the forecast parameters there. So just the way this works real quick, you download some upper data. This is really old data here for 1975, but you can see the maps that the soundings that it produces right there. And you've got all these options here. Soundinggram, layer analyzer, frontal analysis, photograph, mountain wave. There's just some great stuff there. But I think there's a demo available that you can download. It's from rayab.com. And if you buy the program, yeah, just let them know that I sent you over there. Let's see, the massive wedge, Greensburg, Kansas, with 2007. Yeah, that was a bad storm. Just as a bonus, I'll show you a little bit of, I'll just show you one frame of Greensburg here. Greensburg. I can't remember the exact time that tornado hit. 2:37. Yeah, I think I got it right there. Okay, so this is southeast of Dodge City. Yep, there it is. Bad storm there south of Greensburg. And we've got the tornado emergency right there, man. Yeah, we'll take a look at the storm relative velocity. and it's very high. So we've got outbound of 60 knots here, one of 70. We have inbound of 124. Let me show you this real quick. Yeah, there it is. There's the inbound of 124 right there. And I still think the El Reno storm back in 2013, the one that got Carl Young and Tim Samaras, that one was worse. I saw higher velocities in that storm than I did with this one. So I'm going to put that dot right there. And this was before the high resolution upgrade to the radar, so things look kind of coarse here. I mean, we've really got it good there with these NextRad improvements. But here you can see the hook echo shape and the vortex right there in that RFD region close to the updraft. And we'll take a look at the higher tilts. Maybe a little bit of a hint of a beware there. Let's see, let me drop this marker right into that thing. Yep, that was the vortex there. So we've got 89 in and 80 out. So 90 and 80, that's going to be about 170 knots of gate-to-gate shear right there. And there it is. Massive tornado there south of Greensburg, and there's the town. So the next frame after that, next couple frames, there it goes, up in Greensburg. There's the 0.5. Looks like a bit of a hook coming back like that. Yeah, there's the vortex right there. So this is 95 out and 83, 106 in. Just under 200 knots of gate-to-gate shear. But still, I saw more than that on the El Reno storm, but these were both very bad. So there's that cell. Looks like the spectrum width picking up debris right there. So we can back that up and see if we can check that out. So that's another way you can forecast, or when you have an embedded tornado inside a precip area, you can use spectrum width to kind of pull out detail like that. Very unmistakable here. Okay, let me pull up the last few frames here. It's going to be 0246. Okay, this would be the storm coming into town. There's the vortex right there. 120 knots in and 101 out. So it's about 215 knots right there. And at this point we can see that we've seen a little bit of movement to the west through here, it looks like. So highest velocity. Yeah, these are all outbound and these are inbound right there. So vortex right there on the north side of Greensburg. Right there at the tip of that cusp of that hook echo. And right there in that debris cloud. You can kind of track that debris a little bit over the next few frames. So, yeah, that's the Greensburg tornado. Anyway, I didn't want to end things on a dismal note, but it is very interesting from a meteorological standpoint. That was kind of Kansas's own El Reno. And definitely a storm there worth studying. All right, let me look at the chat here. Okay. Greensburg was the pitch black of night from Ryan Toomey's there. El Reno is daylight, so you could see the vortex. Yeah. Okay, well, anyway, that's probably about all I'm going to do for today. I'm going to take care of this pizza here. And anyway, I hope you guys enjoyed the webcast, and we will see you. I don't know if I'm going to do I might do a very short broadcast tonight, but we'll see how it goes. Anyway, take care, and we'll see you next severe weather event.